Millions of years ago, a single volcanic eruption may have pushed humanity to the edge of extinction. Some scientists believe it reshaped our evolution forever, while others argue the evidence tells a very different story. What really happened when one of Earth's greatest supervolcanoes erupted? Could this forgotten catastrophe explain why so few humans survived and why we're here today? In this documentary, we'll uncover the science, the mystery, and the surprising clues hidden beneath layers of ancient ash. If you enjoy exploring humanity's greatest mysteries, don't forget to like, subscribe, and turn on notifications so you never miss our next journey into the distant past. Let's begin. The silence arrives first. Long before any written language exists to describe it, before cities rise beside rivers or monuments cast their shadows across deserts, there stands an immense mountain, unlike the countless volcanoes scattered across the planet. It dominates a tropical landscape where dense forests stretch across rolling hills. Rivers carve their way through fresh volcanic rock, and small bands of early humans move carefully through a world that appears permanent. Nothing about the scene suggests that beneath this peaceful surface lies enough energy to alter the story of an entire species. The mountain is part of a restless earth. Far below the forests, enormous slabs of crust continue their patient collision, descending into the mantle where unimaginable heat transforms solid rock into molten material. Over hundreds of thousands of years, pressure slowly accumulates. Magma chambers expand deep beneath the surface, hidden from every living creature. Trees continue growing. Animals migrate with the seasons. Generations of humans are born and disappear without ever suspecting that the ground beneath their feet is quietly preparing one of the greatest geological events of the last several million years. The landscape itself offers almost no warning. There are earthquakes perhaps, but earthquakes are common in many parts of the ancient world. Hot springs bubble from the earth. Strange gases escape from cracks in isolated valleys. Occasionally smaller eruptions darken the sky for a few days before life resumes its familiar rhythm. Nature appears unpredictable yet ultimately dependable. Few events seem capable of changing the world beyond the horizon. For the small populations of Homo sapiens living across Africa, survival already demands constant adaptation. Every day depends upon finding water before the dry season lengthens. Every journey requires avoiding powerful predators. Every successful hunt depends on cooperation, memory, and careful observation of changing landscapes. These people possess remarkable intelligence, but they remain few in number. The total population of modern humans across the planet may consist of only several thousand breeding individuals scattered across enormous distances. Vast regions remain completely empty of human presence. Their world feels limitless because no individual can ever experience more than a tiny fraction of it. Mountains beyond distant horizons might as well belong to another universe. Forests disappear into endless green walls. Rivers seem eternal. Oceans form boundaries few have ever imagined crossing. News travels only as fast as people walk, and many communities never meet one another at all. Yet the earth connects every landscape through systems invisible to those who inhabit them. Winds carry dust across continents. Ocean currents redistribute heat across hemispheres. Tiny particles released into the atmosphere can eventually influence climates thousands of kilometers away. A volcano does not need to destroy a village directly to transform the lives of those who survive far beyond its reach. Before we go deeper, take a moment to like the video and subscribe if this is the kind of history and mystery you enjoy. Among all known volcanoes, only a handful deserve the description of supervolcano. These are not ordinary mountains that occasionally release lava down their slopes. They are colossal geological systems capable of ejecting thousands of cubic kilometers of ash and volcanic material during a single catastrophic event. Such eruptions occur extremely rarely, separated by hundreds of thousands or even millions of years. Human civilization has never witnessed one. Every historical eruption, no matter how devastating, appears modest beside their potential. The volcano that becomes central to this story lies on what is now the Indonesian island of Sumatra. Today it forms a vast basin occupied by Lake Toba, one of the largest volcanic lakes on Earth. Visitors see peaceful blue water surrounded by steep green hills, villages perched along the shoreline, and forests alive with birds and insects. It is difficult to imagine that this tranquil lake marks the collapsed roof of an enormous magma chamber that once exploded with astonishing violence. Modern geological research reveals the scale only gradually. Thick deposits of volcanic ash appear not merely around Sumatra, but across South Asia, the Indian Ocean, and even parts of eastern Africa. Marine sediment cores preserve microscopic volcanic particles carried thousands of kilometers through the atmosphere. Layers of ash become time markers embedded within ancient landscapes, allowing scientists to reconstruct an event that occurred roughly 74,000 years ago. The number itself almost resists comprehension. 74,000 years separate the present from that eruption. Entire civilizations have risen and disappeared many times over within a much shorter span. Agriculture has existed for barely 1/6 of that interval. Writing occupies only the final moments of this immense timeline. Looking back toward the eruption means entering a world where nearly everything familiar vanishes. The animals are different. Woolly rhinoceroses roam colder regions farther north. Giant mammals still inhabit many continents. Ancient elephants move across forests unlike those surviving today. Alongside modern humans live other members of the human family, including Neanderthals in Europe and Western Asia, while mysterious Denisovans occupy parts of Asia that scientists are only beginning to understand through fragments of ancient DNA. Humanity itself exists at a crossroads. Homo sapiens has evolved, but the species has not yet spread across every continent. Australia may only recently have been reached, depending on the exact timeline scholars reconstruct. Europe remains largely occupied by Neanderthals. The Americas lie completely untouched by humans. The future dominance of Homo sapiens is far from guaranteed. Looking backward from the modern world creates an illusion of inevitability. It is tempting to believe that our species was always destined to succeed, that every obstacle simply delayed an outcome already written into history. The evidence suggests something very different. Evolution offers no guarantees. Countless successful species disappear. Entire branches of the human family vanish without descendants. Survival often depends upon circumstances beyond intelligence alone. That uncertainty makes the Toba eruption so compelling. For decades, researchers have debated whether this single geological catastrophe nearly erased our species. Some propose that the eruption triggered a dramatic population bottleneck, reducing humanity to perhaps only a few thousand survivors. Others argue that while the eruption was extraordinary, early humans proved more resilient than once believed. New discoveries continue to reshape the discussion, yet no single explanation fully accounts for every piece of evidence. What survives in the geological record certainly confirms one fact beyond serious dispute. The eruption itself ranks among the largest known during the Quaternary period. Ash blankets enormous territories. The volcano collapses into an immense caldera. Atmospheric chemistry changes. Regional ecosystems experience profound disruption. Even if humanity ultimately survives with greater success than some early theories proposed, the Earth itself undergoes a transformation on a staggering scale. Standing beside Lake Toba today, surrounded by calm water reflecting quiet skies, it is almost impossible to reconcile the peaceful landscape with the catastrophe buried beneath it. The silence that now defines the lake conceals a memory written not in stories but in rock ash, ice cores, genetic patterns and scattered archaeological traces. Piece by piece, scientists continue assembling those fragments into a narrative that stretches across continents and generations. It is a story not simply about a volcano but about chance, about a species still young enough to disappear, about climates capable of shifting faster than entire populations can migrate, about landscapes that preserve memories long after every witness is gone. And above all, it is about the unsettling possibility that the future of humanity may once have depended upon surviving a single event hidden deep within the restless heart of the earth. The mountain does not appear suddenly. It is the product of an ancient machine that has been operating beneath Earth's surface for tens of millions of years, powered by forces so vast that even continents become temporary features upon them. While early humans search for freshwater-shaped stone tools and pass knowledge from one generation to the next, the planet itself is engaged in a far slower process. Beneath what is now Indonesia, one immense tectonic plate gradually sinks beneath another, carrying seawater sediments and oceanic crust deep into the mantle. The descent is measured in centimeters each year, yet over geological time those centimeters accumulate into hundreds of kilometers, feeding one of the most volcanically active regions on Earth. The Indonesian archipelago exists because of this relentless collision. Thousands of islands rise above the sea, forming a great chain of volcanoes known today as the Sunda Arc. Some erupt frequently with modest explosions. Others remain quiet for centuries before releasing powerful bursts of ash and lava. Yet hidden among these ordinary volcanic systems are a handful of giants, whose behavior follows entirely different rules. Rather than venting pressure through repeated small eruptions, they can store molten rock underground for astonishing lengths of time, allowing enormous reservoirs of magma to grow before eventually failing all at once. The future Lake Toba belongs to this rare category. Long before its most famous eruption, the region has already experienced multiple episodes of volcanic activity. Ancient lava fields spread across the landscape. Earlier calderas collapse and gradually refill with vegetation. New magma intrudes beneath old volcanic structures, recycling the same region again and again. The volcano evolves through a series of immense pulses rather than a single lifetime each episode, reshaping the terrain while laying the foundation for the next. Deep underground, the magma chamber expands with extraordinary patience. It is not a glowing underground lake as popular imagination often suggests, but a complex mixture of molten rock crystals, dissolved gases, and partially solidified material. Temperatures exceed 700 degrees Celsius in some zones and climb much higher in others. The chamber breathes over thousands of years. Fresh magma rises from below, adding heat and volatile gases. Older magma cools along the margins while remaining partially molten near the center. Pressure builds almost imperceptibly. As this process continues, dissolved gases become increasingly important. Water vapor, carbon dioxide, sulfur compounds, and other volatile elements remain trapped under immense pressure. Their behavior resembles the carbon dioxide dissolved inside a sealed bottle of sparkling water, except the scale is almost beyond imagination. As long as the surrounding rock remains strong enough to contain them, the gases stay compressed. Once fractures begin to form, the balance changes dramatically. Expanding gases transform molten rock into an explosive mixture capable of fragmenting entire mountains. Exactly what finally destabilizes the system remains uncertain. Scholars still debate whether fresh injections of hotter magma trigger the eruption, whether gradual overpressure eventually exceeds the strength of the surrounding crust, or whether regional earthquakes contribute to the final failure. The evidence remains incomplete because the crucial events occur kilometers beneath the surface, leaving only indirect clues behind. Modern monitoring of active volcanoes provides valuable comparisons, yet no instrument existed 74,000 years ago to record the final stages beneath Toba. Above ground, life continues almost oblivious to the danger. Tropical forests flourish under warm rainfall. Towering trees shelter countless birds, insects, reptiles, and mammals. Orangutans' distant ancestors move through the canopy. Rivers carry volcanic minerals that enrich surrounding soils, making the landscape remarkably fertile. Many of the world's most productive agricultural regions today owe their richness to ancient volcanic deposits, and the same principle applies in this prehistoric environment. Volcanoes often nurture life for thousands of years before suddenly threatening it. Small groups of Homo sapiens almost certainly occupy parts of eastern Africa at this time, while others gradually disperse into southern Asia. Their camps leave only faint traces, scattered stone flakes, butchered animal bones, patches of charcoal where controlled fires once burned. Most organic materials disappear long before reaching the present. What remains is frustratingly incomplete, forcing archaeologists to reconstruct entire ways of life from fragments preserved by exceptional circumstances. These early humans possess abilities that distinguish them from nearly every other species. They communicate through increasingly sophisticated language, although its exact form remains unknowable. They manufacture carefully shaped stone tools using techniques refined across generations. They cooperate in hunting, gather edible plants across diverse environments, and adapt with remarkable flexibility. None of these advantages, however, make them immune to environmental catastrophe. Intelligence improves the odds of survival, but it does not eliminate vulnerability. The wider world is also changing in subtle ways. Earth's climate during the late Pleistocene fluctuates between colder and warmer intervals, driven largely by slow variations in the planet's orbit and rotation. Glaciers advance and retreat across higher latitudes. Sea levels rise and fall accordingly, exposing land bridges that periodically connect islands and continents, before disappearing beneath returning oceans. These natural oscillations already challenge both animals and humans, requiring constant adaptation to shifting habitats. Against this background of ongoing climatic change, the growing magma chamber beneath Toba represents an additional source of instability. Geological processes and biological evolution unfold simultaneously, occasionally intersecting in ways that redirect the course of history. Most volcanic eruptions remain regional events. Even powerful historical eruptions such as Tambora in 1815 or Krakatoa in 1883 influence global climate only briefly, despite causing immense local destruction. Toba belongs to a different category altogether. Its scale pushes scientists to ask whether a single eruption could alter the trajectory of an entire species. The volcano itself offers occasional hints that something unusual is happening. Ground deformation may slowly lift portions of the landscape as magma accumulates below. Earthquakes likely become more frequent, though no human observer recognizes them as part of a larger pattern. Hot springs may change temperature or chemistry. Gases seep from cracks that were previously quiet. Animals could respond to subtle environmental shifts, abandoning certain valleys or altering migration routes. Such behaviors are observed before some modern eruptions, although they are inconsistent and difficult to interpret. Whether similar signs preceded Toba can never be known with certainty. Time continues its steady march. Decades become centuries, centuries become millennia. Pressure increases one small increment after another, until the surrounding crust approaches its breaking point. The immense chamber beneath Sumatra contains hundreds, perhaps thousands of cubic kilometers of eruptible magma. It is one of the largest accumulations of molten material known to have existed beneath Earth's surface during the recent geological past. Then at some moment impossible to identify in advance equilibrium finally fails. A fracture opens somewhere above the chamber. Compressed gases begin expanding with explosive force. One crack rapidly becomes many. The mountain that has appeared permanent for countless generations enters the first moments of a transformation that will unfold with astonishing speed. The geological clock that has been counting silently for hundreds of thousands of years reaches its final seconds, and the sleeping giant beneath the forests of Sumatra begins to awaken. The first explosion is unlikely to be the largest. Supervolcanoes do not always announce themselves with a single instantaneous blast. Instead, the opening stages may unfold over hours or days as the crust fractures above the immense magma chamber. Each rupture releases more pressure, allowing dissolved gases to expand with extraordinary violence. What begins as a series of colossal explosions rapidly grows into an eruption, unlike anything any human has ever witnessed before or since. Within minutes, columns of ash and pulverized rock climb through the atmosphere at astonishing speed. They rise far beyond ordinary storm clouds, punching deep into the stratosphere, where powerful winds seize the volcanic debris and begin carrying it across continents. Lightning flashes continuously inside the towering eruption column as billions of ash particles collide, generating enormous electrical charges. Thunder echoes through valleys already trembling from relentless earthquakes. The sky itself seems to come apart. Near the volcano, survival quickly becomes impossible. Pyroclastic density currents surge outward from the collapsing eruption column at speeds that can exceed several hundred kilometers per hour. They are not rivers of lava as popular imagination often suggests, but avalanches of incandescent gas volcanic ash, shattered rock and superheated air. Temperatures remain hot enough to ignite forests instantly. Entire hillsides vanish beneath churning grey clouds that erase every living thing in their path. Trees that have stood for centuries snap like dry reeds. Rivers disappear beneath layers of volcanic debris. Animals flee in every direction, only to find escape routes cut off by fresh surges arriving from different valleys. The landscape changes faster than any creature can understand. Within hours, ecosystems that required thousands of years to develop cease to exist. As the eruption intensifies, vast sections of the magma chamber empty with astonishing speed. The mountain can no longer support its own weight. Instead of growing taller through accumulating lava, the volcanic summit begins collapsing inward. Massive blocks of crust sink into the partially evacuated chamber below, creating an enormous depression known as a caldera. The future Lake Toba is born not through gradual erosion, but through catastrophic collapse on a scale almost beyond comprehension. Modern geological reconstructions suggest that the eruption ejects roughly 2,800 cubic kilometers of volcanic material, although precise estimates continue to be refined as new studies emerge. Even conservative calculations place Toba among the largest known eruptions of the Quaternary period. By comparison, the eruption of Mount St. Helens in 1980 releases about 1 cubic kilometer of material. Tambora, whose eruption produces the famous Year Without a Summer, in 1816 ejects roughly 150 cubic kilometers. Toba exceeds both by an extraordinary margin. The numbers alone, however, fail to capture what such an eruption actually means on the ground. Ash does not simply fall like ordinary dust. Close to the volcano, it accumulates with astonishing speed, burying forests beneath meters of hot debris. branches collapse under the growing weight. Lakes become thick grey slurries. Streams clog with sediment until their channels disappear altogether. Every breath becomes dangerous as microscopic volcanic particles fill the air. For any human communities living within hundreds of kilometres, direct survival is extraordinarily unlikely. Archaeological evidence from this immediate region remains sparse, partly because later volcanic activity has repeatedly transformed the landscape. What survives in the geological record suggests devastation on a nearly unimaginable scale. Yet the eruption's influence does not stop where the pyroclastic flows end. Its greatest reach begins only after the explosions themselves. High above the Earth, the eruption column continues spreading outward. Fine volcanic ash circles the globe on powerful atmospheric currents. Larger fragments settle first across Southeast Asia, covering broad regions in thick grey blankets. Farther west, ash eventually reaches the Indian subcontinent, where deposits several meters thick are still preserved in some locations. Even thousands of kilometers away, microscopic volcanic particles drift downward onto distant forests, grasslands, rivers, and coastlines. One of the remarkable discoveries made by modern geologists is the extraordinary consistency of this ash layer. Known as the youngest Toba tuff, it acts almost like a timestamp preserved across enormous distances. Researchers find its distinctive chemical signature in marine sediment cores recovered from the Indian Ocean, in terrestrial deposits across South Asia, and in scattered locations extending toward eastern Africa. These ash layers allow scientists to synchronize ancient environmental records that would otherwise remain disconnected. The atmosphere itself undergoes profound transformation. Along with ash, the eruption releases immense quantities of sulfur dioxide and other volcanic gases into the stratosphere. There, sulfur compounds react with water vapor to form tiny sulfate aerosols. Unlike heavier ash particles that settle relatively quickly, these microscopic droplets can remain suspended for months or even years, reflecting incoming sunlight back into space. Daylight begins to change. Regions close to the eruption experience skies so dark that ordinary distinctions between day and night become difficult to recognize. Farther away, the effect is more subtle but no less significant. Sunrises appear strangely muted. The light filtering through the atmosphere takes on unfamiliar colors. Seasonal patterns become increasingly difficult to predict as solar energy reaching Earth's surface declines. Plants respond almost immediately. Photosynthesis slows beneath dimmer skies. Some species withstand the change better than others, but entire food webs begin experiencing stress. Herbivores struggle where vegetation declines. Carnivores soon face dwindling prey. Rivers receive enormous loads of volcanic sediment, altering aquatic ecosystems, already coping with changing temperatures and reduced sunlight. For early humans, these environmental disruptions unfold without explanation. There is no concept of atmospheric chemistry, no understanding of stratospheric circulation, no knowledge that the strange darkness originates from a mountain, perhaps thousands of kilometers away. Communities simply observe familiar landscapes becoming increasingly unfamiliar. Hunting routes fail, water sources change, seasonal migrations of animals become unpredictable. Some edible plants disappear while others emerge in unexpected places. Yet even amid catastrophe, survival is not equally impossible everywhere. Geography matters, wind direction matters, distance matters. Thick ash blankets one region, while another receives only a light dusting. Coastal environments continue providing marine resources even as inland ecosystems deteriorate. Some valleys retain flowing water, while others become buried beneath sediment. The eruption creates not a single uniform disaster, but a mosaic of different environmental challenges stretching across continents. This uneven pattern will later become central to one of the greatest scientific debates surrounding Toba. If the eruption truly pushes humanity toward extinction, how do scattered populations endure? If human numbers remain relatively stable, why do certain genetic patterns appear to suggest otherwise? The evidence survives only in fragments, and those fragments often point toward different conclusions. For now, however, none of those future debates exist. The eruption is still unfolding. The skies remain heavy with ash. Forests continue disappearing beneath grey deposits. The newly collapsed caldera smoulders where an immense mountain once stood. Across much of southern Asia, countless living creatures face an altered world before they have even begun to understand that the old one has vanished. The greatest explosion is over, but its consequences are only beginning. The ash that now settles silently across distant landscapes carries with it the power to reshape climates, ecosystems, and perhaps even the evolutionary journey of the human species itself. Long after the explosions fade and the eruption column finally begins to collapse, the volcano continues changing the world from thousands of kilometers away. The greatest danger no longer comes from rivers of ash racing down mountainsides or forests, consumed by scorching pyroclastic flows. It now drifts invisibly through the upper atmosphere, carried by powerful winds that know nothing of coastlines, mountains, or the scattered communities struggling below. The eruption has ended, but its influence has only begun. The stratosphere becomes a vast reservoir of microscopic sulfate aerosols formed from the immense quantities of sulfur dioxide released during the eruption. These tiny droplets are remarkably effective at reflecting sunlight back into space. Unlike ordinary weather systems that remain confined to the lower atmosphere, the stratosphere is relatively dry and stable, allowing volcanic aerosols to linger far longer than ash falling through the troposphere. The result is a subtle but persistent reduction in the amount of solar energy reaching Earth's surface. Scientists have witnessed smaller versions of this process in modern times. When Mount Pinatubo erupted in 1991, global temperatures fell by roughly 0.5 degrees Celsius for more than a year. Crops responded, rainfall patterns shifted, sunsets became unusually vivid across much of the world. Yet Pinatubo, despite being one of the 20th century's largest eruptions, released only a tiny fraction of the material associated with Toba. Scaling that comparison upward is not straightforward, but it illustrates how a volcano can influence climates far beyond the reach of falling ash. Exactly how much cooling followed the Toba eruption remains one of the most actively debated questions in quaternary science. Early climate models suggested an extraordinarily severe volcanic winter with average global temperatures dropping by several degrees and some regional temperatures falling much more dramatically. According to these reconstructions, growing seasons would have shortened sharply, rainfall patterns would have shifted, and ecosystems already adapted to fluctuating ice age climates would have faced additional stress unlike anything experienced for thousands of years. More recent models paint a more nuanced picture. Improved understanding of atmospheric circulation, aerosol behavior, and ocean heat storage suggests that the cooling may have been significant, but less catastrophic than originally proposed. Some simulations indicate several years of pronounced cooling followed by gradual recovery, while others argue that regional differences were far more important than global averages. The evidence remains incomplete, and no single explanation fully accounts for every environmental record preserved from that distant time. Ice cores drilled from Greenland and Antarctica provide valuable clues, although interpreting them is challenging. These frozen archives preserve layers of ancient snowfall trapping, tiny bubbles of prehistoric air, and microscopic traces of volcanic material. They reveal that Earth's climate around 74,000 years ago is already undergoing natural fluctuations associated with the last glacial cycle. Separating the volcanic signal from ongoing climatic variability requires careful analysis, and scholars continue refining those interpretations as new techniques emerge. Marine sediment cores tell another part of the story. Tiny shells of plankton settle continuously onto the seafloor, preserving chemical signatures that reflect changing ocean temperatures and productivity. Some cores suggest noticeable environmental disruption after the eruption, while others indicate surprisingly resilient marine ecosystems. Oceans possess enormous thermal inertia, allowing them to absorb and redistribute heat more slowly than land surfaces. This buffering effect may have softened some of the eruption's climatic consequences in coastal regions. On land, however, the situation could be far less forgiving. Plants depend directly on sunlight, temperature, and seasonal rainfall. Even relatively modest climatic shifts can reorganize entire ecosystems when sustained over several growing seasons. Grasslands shrink in some areas while expanding in others. Forest boundaries retreat. Wetlands dry out where precipitation declines. Rivers fed by seasonal rainfall fluctuate unpredictably, forcing animals to abandon migration routes followed for generations. Large herbivores respond first because their survival depends upon abundant vegetation. Herds that once grazed across open plains find less food available. Some migrate into unfamiliar territory, increasing competition with established populations. Others decline in number as calves fail to survive difficult seasons. Predators soon experience the consequences as prey becomes scarcer and more widely dispersed. Carnivores capable of traveling long distances adapt more successfully than specialists tied to particular habitats. Human communities occupy an unusual position within this changing world. They are predators, gatherers, scavengers, and opportunistic foragers all at once. Unlike many large mammals, they are not entirely dependent upon a single food source. Fish, shellfish, roots, fruits, seeds, insects, small animals and large game all contribute to survival, depending on local conditions. This remarkable dietary flexibility may prove to be one of the defining advantages of Homo sapiens. Even so, flexibility has limits. A prolonged reduction in plant productivity affects nearly every level of the food web. Fewer fruits appear in familiar seasons. Edible tubers become harder to locate. Grazing animals alter their movements, forcing hunters to travel farther with no guarantee of success. Waterholes that once remained reliable begin shrinking during longer dry intervals. Every successful meal requires more effort than before. The archaeological record hints at these pressures without describing them directly. Stone tools continue appearing in sites across Africa and parts of Asia, suggesting that human populations do not disappear entirely. Yet the record is fragmented. Many campsites vanish beneath later sediments. Organic materials decay. Rising and falling sea levels erase ancient coastlines where many people may have lived. What survives in the record suggests resilience, but it cannot reveal the countless failed journeys, abandoned camps, or desperate decisions that leave no physical trace. Some regions may even experience unexpected opportunities amid widespread disruption. Volcanic ash eventually enriches soils with minerals as it weathers. Newly open landscapes allow certain plant species to colonize disturbed ground. Lakes formed by blocked river valleys create fresh aquatic habitats. Ecological collapse is rarely uniform. Decline in one environment may coincide with expansion in another. Such uneven change creates a constantly shifting mosaic of risks and possibilities. This regional variability becomes increasingly important as researchers compare evidence from different continents. Eastern Africa, often regarded as the primary homeland of Homo sapiens, appears to show continued human occupation through the period surrounding the eruption. Southern Africa also preserves evidence of persistent populations using coastal resources. Meanwhile, parts of India contain archaeological sites, both beneath and above the Toba ash layer, raising intriguing questions about whether local human groups survived the eruption directly rather than recolonizing afterward. These discoveries complicate earlier narratives of near-total extinction. If humans remain present in multiple regions throughout the event, perhaps the volcanic winter is less universally devastating than once imagined. On the other hand, continued occupation does not necessarily imply stable populations. Small surviving groups scattered across favorable refuges could still experience dramatic demographic decline. While leaving archaeological traces that suggest continuity, nature often preserves survival more readily than prosperity. A species does not need to flourish in order to avoid extinction. It merely needs enough individuals occupying enough suitable habitats to endure until conditions improve. The difference between thriving and barely surviving may be almost invisible 74,000 years later. As the years pass, sunlight gradually strengthens. Sulfate aerosols settle from the atmosphere. Temperatures begin recovering toward their previous patterns. Forests slowly reclaim disturbed landscapes. Rivers establish new channels through thick volcanic sediments. Animals expand back into territories abandoned during the harshest years. Yet the world that emerges is not identical to the one that disappeared beneath the ash. Every surviving population now carries the memory of environmental instability, whether preserved in genes, behavior, migration routes, or landscapes forever altered by one of Earth's greatest eruptions. The volcanic winter does not arrive everywhere with equal force, nor does it test every human community in the same way. Some groups experience skies dimmed by drifting ash. Others confront seasons that no longer behave as memory expects, and still others find themselves living at the edge of landscapes that have become strangely unfamiliar. There is no single human story unfolding after the eruption. Instead, thousands of individual struggles play out across an enormous geographic stage, most leaving no trace except the fact that descendants exist today. At this point in prehistory, Homo sapiens remains an uncommon species. Modern humans have developed remarkable cognitive abilities, but they have not yet become the dominant force that will eventually reshape every continent. Population densities are extraordinarily low. A family may travel for weeks without encountering another group. Entire valleys remain untouched by human footprints. Vast forests, deserts, and grasslands stretch across the planet with almost no permanent human presence. This sparse distribution creates both vulnerability and opportunity. A disease cannot spread rapidly through isolated communities, but neither can knowledge. If one region discovers a more effective hunting strategy or a new source of edible plants, that information rarely travels beyond neighboring groups. Every community depends primarily upon its own accumulated experience, passed through observation, imitation, and increasingly sophisticated language. The eruption places those local traditions under immense pressure. Animals no longer appear where they are expected. A river that reliably supports fish each dry season begins flowing differently after volcanic sediment alters its course. Trees that once produced predictable harvests of fruit fail to flower on time. Familiar migration routes disappear as grazing animals respond to changing vegetation. Knowledge carefully built across generations suddenly becomes less reliable. For early humans, uncertainty itself becomes one of the greatest threats. Unlike many predators, Homo sapiens does not possess extraordinary physical strength, exceptional speed, or natural weapons capable of overcoming large prey alone. Survival depends instead upon anticipation. Hunters succeed because they know where animals usually travel. Gatherers fill baskets because they remember which valleys produce edible roots after seasonal rains. Parents protect children because experience teaches where danger normally waits. When environmental patterns shift, that accumulated knowledge loses part of its value. A hunting expedition that would once have guaranteed success may now return empty-handed. Waterholes remembered since childhood may stand nearly dry. Forests may remain standing while producing far less food than before. These changes unfold gradually enough that no single day announces catastrophe, yet quickly enough to disrupt expectations formed over entire lifetimes. Some communities almost certainly fail to adapt. The archaeological record rarely preserves evidence of unsuccessful survival. When a small band disappears, few traces remain beyond scattered stone tools gradually buried beneath soil. No monuments record their existence. No written histories preserve their names. Entire family lineages vanish without leaving descendants. Their disappearance becomes invisible except as part of humanity's overall demographic history. Others respond with remarkable flexibility. One of the defining characteristics of Homo sapiens is behavioral adaptability. Rather than relying upon a single food source, humans exploit astonishingly diverse environments. Along coastlines, shellfish, fish, seabirds, and marine mammals provide dependable nutrition, even when inland ecosystems fluctuate. In forests, edible nuts, fruits, insects, and small animals supplement larger game. Grasslands offer different opportunities, while wetlands provide still others. This ecological versatility may prove more valuable than any individual technological innovation. Coastal regions receive particular attention from modern researchers because they offer relatively stable food supplies. Marine ecosystems respond differently to climatic disruptions than terrestrial ones. Ocean temperatures change more slowly, and tidal resources remain available regardless of shifting rainfall patterns inland. Shell middens discovered at several South African archaeological sites suggest that some human groups increasingly exploit coastal resources during periods of environmental stress. These ancient shorelines, however, present one of archaeology's greatest challenges. 74,000 years ago, global sea levels are substantially lower than today because enormous quantities of water remain locked inside continental ice sheets. Many prehistoric coastlines now lie beneath the ocean, hidden beneath meters of seawater and sediment. If large numbers of humans survive along those ancient shores, much of the evidence may remain permanently inaccessible. What appears to be an incomplete archaeological record may partly reflect landscapes that have simply disappeared beneath rising seas. Inland communities face different challenges. Large mammals remain important sources of protein, fat, hides, and bone, but successful hunting requires careful coordination. Spears must be manufactured from suitable wood. Stone points require skillful shaping. Tracking wounded animals demands experience and patience. During times of ecological disruption, every failed hunt carries greater consequences because replacement opportunities become less predictable. Gathering becomes equally demanding. Many edible plants produce food only during narrow seasonal windows. Missing those opportunities can have serious consequences, especially if climate shifts alter flowering or fruiting times. Experienced gatherers must constantly update their understanding of changing landscapes. Children learn not merely established traditions, but the ability to recognize when those traditions no longer match reality. Fire becomes even more valuable than before. Beyond warmth and protection, controlled fire expands the range of edible foods. Tough roots become digestible after cooking. Meat lasts longer when smoked. Certain toxic plants become safe only after prolonged heating. Fire also allows humans to occupy cooler environments that might otherwise prove inhospitable during temporary climatic deterioration. Although archaeological evidence cannot always determine precisely how these practices evolve, The importance of controlled fire almost certainly increases whenever environmental conditions become more challenging. Social cooperation may become humanity's greatest survival tool. No individual possesses complete knowledge of every resource available across a changing landscape. Different families remember different water sources. Hunters recognize different migration routes. Gatherers specialize in different plant communities. Sharing information dramatically improves collective resilience, particularly when familiar environments become unpredictable. Anthropologists studying modern hunter-gatherer societies frequently observe extensive food sharing, reciprocal support, and flexible social networks extending beyond immediate families. While direct comparisons must be made cautiously, many researchers believe similar behaviors likely characterize late Pleistocene Homo sapiens. During periods of scarcity, cooperation often provides advantages that solitary survival cannot match. Evidence also suggests that human mobility increases during environmentally stressful periods. Rather than remaining permanently attached to specific territories, groups may travel farther in search of reliable resources. Seasonal movements become more extensive. Temporary camps replace longer occupations. Exchange between neighboring populations may become increasingly important as communities seek information about distant landscapes. Such mobility leaves scattered archaeological traces rather than concentrated settlements, making ancient populations appear smaller than they actually are. Yet movement carries risks. Unknown territories contain unfamiliar predators, competing human groups and water sources whose seasonal reliability remains uncertain. Every migration represents a gamble between staying in a deteriorating environment and entering one whose conditions cannot be fully predicted. Some journeys undoubtedly succeed. Others likely end in failure that archaeology can rarely document. Meanwhile, children continue to be born into this altered world. For the youngest generation, diminished forests, cooler temperatures, and shifting animal migrations are not signs of disaster, but simply the world as it exists. Human memory extends only a few generations. Landscapes that older adults remember vividly become stories to those born after the eruption. Adaptation therefore occurs not only through survival, but through changing expectations. Humanity gradually learns to live inside a world transformed by forces beyond its comprehension. This quiet resilience may ultimately prove more significant than dramatic heroism. No great leader directs humanity's response. No coordinated migration unites continents. Survival emerges instead from countless ordinary decisions made by small communities, choosing one valley instead of another, following a different herd, collecting unfamiliar plants, sharing food during difficult seasons, teaching children new patterns instead of old ones. History often celebrates extraordinary moments, but evolution is more frequently shaped by ordinary choices repeated thousands of times. Whether these adaptations are enough to preserve the species remains uncertain. Population numbers may still be falling. Entire regions may already have lost most of their inhabitants. Somewhere beyond the surviving camps, empty landscapes testify to communities that never recover. The greatest question now confronting modern science is whether humanity merely endures this catastrophe or comes astonishingly close to disappearing forever. The idea is both unsettling and strangely elegant. A single volcanic eruption occurs on a distant island, darkens the skies, disrupts climates across much of the planet, and leaves humanity balanced on the edge of extinction. Thousands of generations later, every person alive carries within their DNA the faint signature of that narrow escape. It is a story that seems almost perfectly designed for documentaries and popular science books. Yet science rarely rewards stories simply because they are compelling. It rewards those that survive relentless testing and the hypothesis connecting Toba to a dramatic human population collapse has spent decades under exactly that kind of scrutiny. The concept becomes widely known as the Toba catastrophe theory. During the 1990s, several researchers proposed that the eruption triggers a severe volcanic winter, lasting years, perhaps even decades. Food supplies decline across enormous regions. Animal populations shrink. Human communities fragment into isolated refuges. According to this interpretation, the total breeding population of Homo sapiens may fall to only a few thousand individuals, or perhaps even fewer. The idea immediately attracts attention because it appears to solve another scientific puzzle that has long intrigued geneticists. Compared with many other large mammals, modern humans possess surprisingly low genetic diversity. Two unrelated chimpanzees living in neighbouring forests can sometimes differ genetically more than two humans born on opposite sides of the world. This limited variation suggests that at some point in the past, humanity passed through what biologists call a population bottleneck, a period when relatively few individuals contributed genes to future generations. Population bottlenecks occur in many species. A disease outbreak, prolonged drought island isolation, or rapid environmental change can dramatically reduce numbers. Even if the population later expands, much of its earlier genetic diversity has already disappeared forever. Future generations inherit only the DNA carried by the survivors. The Toba eruption appears to provide a dramatic candidate for such a bottleneck. The timing seems promising. The eruption occurs roughly 74,000 years ago. Early genetic studies estimate that modern human populations may have experienced a significant demographic contraction, somewhere between 50,000 and 100,000 years ago. The chronological overlap encourages researchers to ask whether these two events are connected. At first glance, the hypothesis appears remarkably persuasive. A supervolcanic eruption is capable of altering global climate. Environmental disruption reduces food availability. Smaller human populations become increasingly vulnerable. Survivors remain isolated in scattered refuges before gradually expanding once conditions improve. The broad outline seems plausible, and for several years the theory receives considerable attention, both within scientific circles and among the general public. Then the evidence begins to grow more complicated. Genetics advances rapidly during the early 21st century. New sequencing technologies allow researchers to examine entire genomes rather than limited genetic markers. Ancient DNA recovered from prehistoric human remains provides additional information unavailable to earlier generations of scientists. Statistical models become more sophisticated, incorporating mutation rates, migration patterns, and changing population structures with increasing precision. Instead of producing one clear answer, these advances reveal a far more intricate picture. Some genetic analyses continue to support the existence of a substantial bottleneck during the late Pleistocene. Others suggest that population reductions occur earlier or later than the Toba eruption. Still others argue that the apparent bottleneck reflects gradual demographic processes unfolding over tens of thousands of years rather than one catastrophic event. The timing itself becomes surprisingly difficult to pin down. Genetic clocks estimate past population sizes by measuring accumulated mutations across generations. Yet mutation rates vary slightly between studies. Different statistical assumptions produce different timelines. Small adjustments can shift estimated bottlenecks by thousands of years, making direct comparison with the eruption increasingly uncertain. Meanwhile, archaeology introduces additional challenges. If humanity is reduced to only a few thousand individuals, worldwide researchers might expect widespread abandonment of archaeological sites immediately after the eruption. Instead, discoveries from several regions suggest greater continuity than anticipated. One of the most important examples comes from the Indian subcontinent. At sites such as Jwalapuram in southern India, archaeologists uncover stone tool assemblages lying both beneath and above the toba ash layer. Remarkably, the technology appears broadly consistent across the volcanic boundary. This raises an intriguing possibility. Rather than disappearing completely and being replaced later by migrants, local human populations may have survived the eruption in place. Exactly what this evidence means remains actively debated. Some scholars argue that technological continuity strongly supports uninterrupted occupation. Others caution that similar stone tools do not necessarily prove the same. Populations remain present. Different groups facing comparable environmental conditions can independently produce comparable technologies. The evidence remains suggestive rather than conclusive. Research from Africa presents another important perspective. Eastern and southern Africa preserve numerous archaeological sites indicating continued human occupation through the approximate period of the eruption. Some coastal communities appear to exploit marine resources consistently, despite broader climatic fluctuations. These findings imply that certain regions may have functioned as environmental refuges, where survival remains more achievable than in heavily ash-covered landscapes. Climate modelling also evolves. Earlier simulations often assume extremely severe volcanic cooling lasting many years. More recent models incorporate improved understanding of aerosol chemistry, atmospheric circulation, and ocean feedback mechanisms. Several suggest that while cooling is undoubtedly significant, its duration and geographic intensity vary considerably. Some regions experience harsh conditions while others remain comparatively resilient. This emerging complexity shifts the discussion away from simple either-or conclusions. Perhaps the eruption does not nearly exterminate every human population. Equally, perhaps it is far more disruptive than a temporary inconvenience. Nature rarely conforms to extremes. Environmental crises frequently produce uneven consequences depending upon geography, ecology, and the adaptability of local populations. Modern anthropologists increasingly emphasize resilience rather than uniform collapse. Human beings occupy extraordinarily diverse habitats even during the late Pleistocene. Forests, savannas, coastlines, river valleys, and upland regions each respond differently to climatic disturbances. Communities relying upon coastal shellfish may endure conditions that devastate inland hunters dependent upon grazing mammals. Small connected populations may recover more rapidly than isolated ones. Flexibility itself becomes part of the explanation. Another possibility also emerges. Rather than causing the bottleneck directly, toba may intensify demographic pressures already underway. Earth's climate is fluctuating throughout this period as glacial cycles continue reshaping habitats. Human populations remain relatively small long before the eruption. Migration competition, local extinctions, and environmental variability may all contribute to reducing genetic diversity over extended periods. In this interpretation, the volcano becomes one important event within a much longer evolutionary story rather than its sole driving force. No single explanation fully accounts for every observation. Genetic evidence points toward reduced ancestral population sizes. Archaeological discoveries demonstrate surprising continuity in several regions. Geological records confirm an eruption of extraordinary magnitude. Climate reconstructions indicate meaningful environmental disruption, while differing over its exact severity. Each line of evidence tells part of the story, yet none alone provides a complete narrative. Perhaps that is the most valuable lesson offered by the toba debate. Science advances not by defending attractive ideas, but by challenging them repeatedly. The original catastrophe hypothesis stimulates decades of new fieldwork. Improved climate models, expanded genetic research, and fresh archaeological discoveries across multiple continents. Even where early conclusions require revision, the questions themselves lead to a deeper understanding of both Earth's history and humanity's past. The volcano remains one of the greatest eruptions ever identified. The human population almost certainly faces extraordinary environmental pressures during and after the event. Whether those pressures reduce our ancestors to a tiny remnant or simply test a remarkably adaptable species continues to be investigated. Hidden within the genomes of billions of living people and buried beneath layers of ash scattered across continents, the answer is still slowly emerging. If the rocks preserve the memory of the eruption, DNA preserves the memory of survival. Unlike volcanic ash, which settles into ancient lake beds and river valleys, genetic information passes silently from one generation to the next, carrying fragments of an unimaginably distant past inside every living person. It is an archive that exists not in museums or buried ruins, but within billions of cells recording ancestry through patterns that no human could see until the final decades of the 20th century. The first scientists to recognize this hidden archive quickly discovered something unexpected. Human beings are remarkably similar to one another at the genetic level. Across continents, languages, and cultures, the overwhelming majority of human DNA is shared. The visible differences that seem so significant in everyday life represent only a tiny fraction of the genome. Compared with many other species that occupy broad geographic ranges, Homo sapiens possesses surprisingly limited genetic variation. At first, this seems counterintuitive. Modern humans inhabit nearly every environment on Earth. They have adapted to tropical rainforests, Arctic tundra, high mountain plateaus, scorching deserts, and remote Pacific islands. Such global expansion might be expected to produce enormous genetic diversity. Instead, the evidence points toward a relatively recent common ancestry shared by everyone alive today. This does not mean humanity lacks variation. Certain populations carry adaptations to high altitudes, lactose digestion resistance to local diseases, or differences in skin pigmentation, reflecting long-term environmental pressures. Yet beneath these adaptations lies an unmistakable pattern. Modern humans appear to descend from a surprisingly small ancestral population that existed deep in prehistory. Exactly how small remains one of the most debated questions in evolutionary genetics. When researchers discuss an ancestral population of only a few thousand individuals, they're usually referring not to the total number of living humans, but to what geneticists call the effective population size. This concept differs from a simple head count. It estimates how many individuals actually contribute genes to future generations over long periods. A population of tens of thousands may still have a much smaller effective size if only part of it reproduces consistently, or if groups remain isolated from one another. Understanding this distinction is essential because it prevents dramatic misunderstandings. Headlines sometimes claim that humanity once consisted of only 2,000 people alive at one time. The actual scientific picture is far more nuanced. The effective population may have been quite small, while the total number of living humans remained considerably larger. Even so, the genetic evidence still suggests that our ancestors experienced periods of remarkable demographic constraint. Researchers extract this information through several complementary methods. Some examine mitochondrial DNA, which passes almost exclusively from mothers to their children. Others analyze the Y chromosome inherited primarily through paternal lines. Increasingly, scientists compare entire genomes across populations worldwide, identifying subtle patterns of shared ancestry mutation rates and historical population expansion. These studies consistently reveal a story of remarkable interconnectedness. Every person alive today belongs to a family tree whose branches repeatedly merge as one travels backward through time. Eventually, separate lineages converge upon common ancestors who lived tens of thousands of years ago. The farther back the timeline extends, the smaller the ancestral population becomes. Countless family lines simply end, leaving no descendants in the modern world. This gradual disappearance of lineages is a natural consequence of evolution. Imagine hundreds of small human groups scattered across Africa and southern Asia. Some flourish for centuries before fading away. Others merge with neighboring populations. A few become the ancestors of countless future generations. From the perspective of modern genetics, successful lineages become increasingly visible, while extinct ones vanish almost completely. Yet DNA can reveal only so much. Genes preserve information about ancestry, not detailed historical events. A population bottleneck leaves a recognizable signature, but it does not identify its cause. Reduced genetic diversity might result from prolonged climate change, repeated droughts, disease migration, competition between human groups, or combinations of many different pressures. The genome records that something significant happened, but it does not explain why. This limitation explains why connecting genetics directly to the Toba eruption remains challenging. The timing appears broadly compatible, but broad compatibility is not definitive proof. Mutation rates contain margins of uncertainty. Population structures shift over thousands of years. Different statistical models produce different demographic histories. Each improvement in genetic technology sharpens the picture, while simultaneously revealing new layers of complexity. Ancient DNA has transformed this field more than almost any other development. For decades, researchers relied entirely upon living populations to reconstruct prehistoric ancestry. Today, fragments of DNA recovered from ancient bones allow direct comparison with individuals who lived tens of thousands of years ago. These discoveries reveal that prehistoric humanity is far more interconnected than previously imagined. Neanderthals, once regarded as entirely separate from modern humans, are now known to have interbred with Homo sapiens after our species expanded into Eurasia. Most people living outside sub-Saharan Africa today carry small percentages of Neanderthal DNA inherited from those ancient encounters. Denisovans, identified initially from only a tiny finger bone discovered in Siberia, also contributed genes to modern populations, particularly among indigenous peoples of Oceania and parts of Southeast Asia. These discoveries fundamentally reshape the story of human evolution. Rather than replacing every other human species without interaction, Homo sapiens repeatedly encounters distant relatives, exchanges genes with them, and carries fragments of those ancient populations into the present. Human history resembles a braided river more than a single straight line. Interestingly, this complexity also affects interpretations of population bottlenecks. Interbreeding with Neanderthals and Denisovans introduces additional genetic diversity into expanding Homo sapiens populations. At the same time, isolated communities within Africa continue evolving independently, before reconnecting through later migrations. The genetic landscape becomes far richer and more intricate than earlier models could easily represent. Africa itself emerges as a key part of the puzzle. For much of the 20th century, scientists often imagined early Homo sapiens originating from a relatively localized ancestral population. Increasing evidence now suggests a more dynamic picture, involving numerous interconnected populations spread across different African environments. These groups occasionally separate during periods of climatic stress, and later reconnect when conditions improve, exchanging genes across enormous distances. Such population networks may help explain humanity's resilience. If one region experiences severe environmental disruption, neighboring populations occupying different habitats can preserve genetic diversity even while local communities decline. Rather than depending upon a single refuge, Homo sapiens may survive through a mosaic of partially connected populations responding differently to changing climates. This interpretation aligns surprisingly well with archaeological evidence. Stone tool traditions vary across Africa during the late Pleistocene, reflecting regional adaptations rather than complete isolation. Coastal communities exploit marine resources. Inland groups develop different hunting strategies. Some populations occupy grasslands while others remain within forest margins. Diversity exists not only genetically but behaviorally. Scholars still debate exactly how these networks function and how frequently distant populations interact. The evidence remains incomplete because organic materials rarely survive long enough to preserve direct traces of movement. Yet what survives in both genetics and archaeology increasingly suggests that flexibility, mobility, and intermittent connection characterize early Homo sapiens long before civilization appears. Perhaps this is the true message hidden within our DNA. The story is not merely one of survival against overwhelming odds. It is a story of movement rather than permanence, connection rather than isolation, adaptation rather than rigid tradition. Whether the Toba eruption represents the decisive turning point or one challenge among many, the people who endure are not necessarily the strongest or the most numerous. They are those capable of adjusting when familiar landscapes no longer provide familiar answers. Every human alive today carries the outcome of those countless adjustments. Somewhere within the shared patterns of our genomes lies the faint echo of ancient populations that refuse to disappear even as volcanoes reshape continents and climates transform the world around them. Their names are lost forever, but their survival continues in every generation that follows. While DNA preserves the history of inheritance, the ground preserves the history of daily life. Every campsite abandoned beside a river, every stone tool left where it falls, every hearth slowly buried beneath drifting sediment becomes part of an archaeological record stretching back tens of thousands of years. Yet unlike the remarkable continuity of genetic information, archaeology is an incomplete archive. Most traces disappear almost as quickly as they are created. Wood rots, animal hides decay, plant fibers vanish, rain reshapes the soil, rivers carry away entire campsites, forests reclaim clearings within a few decades. By the time 74,000 years have passed, only the smallest fraction of human activity survives. This absence creates one of the greatest challenges in reconstructing the world before and after the Toba eruption. Archaeologists are not searching for cities or temples built from stone. They are searching for the temporary camps of highly mobile hunter-gatherers whose shelters consist largely of branches, leaves, animal skins, and wooden poles. The physical evidence is often no more than scattered flakes of stone left behind during tool-making, broken bones discarded after meals, patches of charcoal from ancient fires, and occasional concentrations of ash marking where people once gathered. Even these fragile traces can vanish beneath a single flood. Entire valleys that may once have supported generations of human occupation are buried beneath layers of sediment deposited over thousands of years. In other places, erosion strips away ancient surfaces, completely carrying away evidence that can never be recovered. Archaeologists therefore work with a record shaped not only by human behavior, but by geological luck. A site survives because it is buried quickly enough to escape destruction, or because changing environmental conditions accidentally preserve it. The Toba eruption introduces another complication. Across large parts of South Asia, volcanic ash becomes a geological timestamp. The youngest Toba tuff forms a distinct layer separating older sediments from younger ones. At first glance, this seems ideal. If archaeologists discover human artifacts beneath the ash, they know people lived there before the eruption. If they find artifacts above it, they know humans returned afterward. The question is what happens in between. For many years, researchers assumed that thick ash deposits imply widespread abandonment. Such an interpretation appears reasonable. A landscape suddenly buried beneath volcanic debris would seem difficult to inhabit. Yet as excavations expand, the picture becomes more complicated. One of the most influential sites lies near Jwalapuram in southern India. Here archaeologists uncover stone tools both below and above the volcanic ash layer. More strikingly, the technologies appear remarkably similar. The methods used to shape stone flakes before the eruption continue afterward with no obvious interruption. This continuity immediately attracts attention. If the eruption completely eliminates local populations who produces the nearly identical tools after conditions improve, one possibility is that new groups migrate into the region carrying similar technological traditions. Another is that at least some of the original inhabitants survived the eruption itself, maintaining cultural continuity despite severe environmental stress. Neither explanation can be accepted uncritically. Stone tools are extraordinarily durable but frustratingly limited in what they reveal. Similar techniques can emerge independently among different populations facing comparable needs. At the same time, technological continuity often reflects cultural continuity. Archaeologists must therefore weigh probabilities rather than certainties. What survives in the record suggests persistence, but the evidence remains incomplete. Elsewhere in India, additional sites contribute new pieces to the puzzle. Some preserve microscopic volcanic ash alongside stone artifacts, allowing researchers to reconstruct changing environments in remarkable detail. Others reveal shifts in animal remains indicating altered hunting patterns after the eruption. No single excavation resolves the debate yet. Together they suggest that human responses vary considerably across different regions. Africa presents a different archaeological landscape altogether. Unlike South Asia, Eastern and Southern Africa receive relatively little volcanic ash directly from Toba. Instead, researchers search for indirect signs of climatic disruption. Caves overlooking ancient coastlines become especially valuable because they often preserve layers of occupation extending across tens of thousands of years. Sites such as Pinnacle Point, Blombos Cave and Sibidu Cave in southern Africa reveal communities displaying impressive behavioral flexibility. Although each site possesses its own unique history collectively, they suggest that Homo sapiens continues occupying coastal environments through periods of climatic instability. Marine shellfish, fish, seabirds, and edible coastal plants provide dependable resources even when inland conditions fluctuate. These discoveries reinforce an important idea. Human survival does not depend solely upon resisting catastrophe. It also depends upon finding places where catastrophe is less severe. Scientists sometimes describe such regions as refugia areas, where environmental conditions remain relatively favorable, while surrounding landscapes become more difficult to inhabit. During Ice Age climate fluctuations, refugia allow plants and animals to persist until broader conditions improve. Increasingly, archaeologists believe similar refuges may play a critical role in human survival. Refugia need not be large. A productive coastline, a river valley supplied by reliable springs, or a sheltered upland with diverse plant life may support populations even while neighbouring regions struggle. Such pockets of stability become stepping stones for later expansion once climates recover. The archaeological evidence also reveals something subtle but important about human behaviour. Stone tool traditions are not static. Across Africa and parts of Asia, archaeologists observe gradual refinements in manufacturing techniques long before agriculture emerges. Certain tools become thinner and more standardized. Others appear designed for specialized tasks such as processing hides, woodworking, or harvesting plant materials. These innovations do not occur everywhere, simultaneously reflecting the remarkable diversity of prehistoric human societies. Some researchers argue that environmental uncertainty encourages experimentation. When familiar resources become unreliable, communities have greater incentive to explore new foods, develop improved hunting methods, or exploit habitats previously considered less desirable. Although direct cause and effect relationships remain difficult to establish, periods of climatic fluctuation often coincide with bursts of technological creativity in the archaeological record. Fireplaces tell another quiet story. Ancient hearths preserved beneath cave floors or buried campsites indicate repeated occupation over many generations. Layers of charcoal, burned bone, and heat-fractured stone reveal communities returning to favored locations despite changing climates. Fire provides warmth, protection, cooking, and social gathering space. It also creates a stable center around which knowledge passes from older generations to younger ones. Perhaps the most remarkable aspect of these archaeological sites is not what they contain, but what they fail to reveal. There is no dramatic horizon marking the end of humanity, no continent-wide layer of abandoned camps, no sudden disappearance of stone tools, no unmistakable break separating one human world from another. Instead, the record shows continuity, interrupted by local disruptions, adaptation, mixed with lost persistence, alongside regional decline. This pattern mirrors what ecologists often observe after natural disasters. Some habitats collapse completely, others recover surprisingly quickly. Species disappear from certain areas while thriving elsewhere. Survival rarely follows a single universal script. Geography shapes outcomes as much as the event itself. The scattered campsites, weathered stone tools, and faint traces of ancient fires therefore tell a quieter but perhaps more profound story than one of near-instant extinction. They suggest that early humans endure not because the eruption spares everyone equally, but because countless small communities respond differently to an unpredictable world. Some vanish forever, others move, some adapt in place. Together, those surviving fragments preserve enough of humanity for the species to continue its extraordinary journey. Buried beneath ash, hidden inside caves, or scattered across forgotten riverbanks, these modest archaeological remains form one of the strongest reminders that history is often written not by spectacular monuments, but by ordinary people whose greatest achievement is simply surviving long enough to leave descendants. The world after the eruption is not equally damaged. From a distance, it is tempting to imagine the catastrophe as a single grey cloud spreading evenly across the planet, bringing identical consequences to every landscape it touches. Nature rarely behaves that way. Mountains redirect winds, oceans absorb heat, rivers continue flowing through sheltered valleys, while neighbouring plains dry beneath altered weather patterns. Forests retreat in one region, even as grasslands expand in another. Survival depends not only on the magnitude of the disaster, but also on where one happens to be when it arrives. This uneven geography becomes one of the most important themes in understanding humanity's response to the Toba eruption. Modern maps can show the extent of volcanic ash deposits with impressive precision, but those maps reveal only part of the story. Ash thickness, local climate, vegetation, water availability, and ecological resilience all interact to produce remarkably different outcomes across the ancient world. Close to Sumatra, the destruction is immediate and overwhelming. Much of northern Sumatra is transformed into a landscape almost beyond recognition. Pyroclastic flows sterilize enormous areas. Thick volcanic deposits bury forests, rivers, and wildlife beneath layers of hot ash and fragmented rock. Even after temperatures fall, the terrain remains deeply altered. New drainage systems begin forming across unstable slopes. Lakes appear where valleys are blocked. Fresh volcanic surfaces slowly weather into fertile soils, but that transformation requires centuries rather than seasons. Farther west across the Indian Ocean, the effects become increasingly indirect. India receives substantial ashfall across broad regions, though the thickness varies considerably. In some places, volcanic material accumulates deeply enough to transform local ecosystems. Elsewhere, only thin layers settle onto existing landscapes before gradually becoming incorporated into the soil. Communities living hundreds of kilometers apart may therefore experience the same eruption in dramatically different ways. For people inhabiting river valleys, ash creates both problems and opportunities. Initially, fine volcanic particles contaminate water sources, making streams cloudy and difficult to use. Heavy rains wash enormous quantities of sediment downstream, altering river channels and burying floodplains. Fish populations may decline temporarily where aquatic habitats become clogged with suspended material. Over longer timescales, however, volcanic minerals enrich surrounding soils. Modern civilizations have repeatedly settled near volcanoes despite their obvious dangers, because weathered volcanic ash often produces exceptionally fertile farmland. Although agriculture will not emerge for many tens of thousands of years, the same geological processes are already at work. Slowly, landscapes devastated by eruption begin supporting renewed plant growth. What first appears lifeless gradually becomes one of the richest ecological environments in the region. The pace of recovery differs enormously. Fast-growing grasses colonize disturbed ground within relatively short periods. Shrubs follow. Pioneer tree species establish themselves where conditions allow. Mature tropical forests require much longer to return, sometimes taking centuries before complex ecosystems resembling the original landscape reappear. Animals respond according to their own ecological strategies. Small mammals capable of reproducing quickly often recover faster than large herbivores with lengthy gestation periods. Birds disperse into newly available habitats with remarkable speed. Insects recolonize disturbed areas almost immediately, helping pollinate recovering vegetation. Predators eventually return as prey populations stabilize. These natural cycles create windows of opportunity for adaptable human groups. Open landscapes may temporarily favor hunting certain species that avoid dense forests. Newly formed wetlands attract waterfowl and fish. Rivers carving fresh channels expose stones suitable for tool-making. Disturbance does not simply remove resources, it reorganizes them. Coastal environments follow an even more distinctive pattern. The oceans continue producing food despite disruptions on land. Shellfish cling to rocky shores. Fish schools migrate through coastal waters according to seasonal rhythms, influenced more by marine ecosystems than by conditions inland. Seaweed seabirds and marine mammals provide additional sources of nutrition. This stability may explain why archaeologists increasingly emphasize coastal refuges in discussions of early Homo sapiens survival. Southern Africa offers especially compelling evidence. Cave sites overlooking what were once ancient shorelines reveal repeated human occupation, extending across periods of considerable climatic fluctuation. Although sea levels differ dramatically from those of today, these communities appear remarkably skilled at exploiting marine resources. Shellfish require no elaborate hunting strategy. Unlike large mammals that migrate unpredictably during environmental stress, shellfish remain attached to tidal rocks. Knowledge of tides and seasonal harvesting often provides dependable food with relatively little risk. Such resources cannot support unlimited populations, but they can help small communities survive difficult years when inland hunting becomes unreliable. Not every refuge lies beside the sea. River systems fed by underground springs continue flowing even during prolonged dry periods. Highland regions sometimes receive rainfall when surrounding lowlands remain parched. Forest patches surviving within broader grassland environments preserve edible plants unavailable elsewhere. The late Pleistocene landscape resembles a patchwork rather than a uniform environment, with each region offering its own combination of challenges and possibilities. Mobility becomes increasingly valuable. Hunter-gatherers are not fixed to permanent settlements. Their ability to move allows them to respond dynamically to changing conditions. If one valley becomes less productive, another may still offer abundant resources. Travel carries obvious risks, yet remaining in a deteriorating landscape may prove even more dangerous. Anthropologists often describe this flexibility as one of humanity's defining evolutionary advantages. Unlike highly specialized species dependent upon narrow ecological niches, Homo sapiens occupies an astonishing variety of habitats. This adaptability stems not from biological changes occurring over generations, but from cultural knowledge transmitted within lifetimes. New hunting strategies, unfamiliar plant foods, improved shelter construction, and revised seasonal movements can all emerge far more rapidly than genetic evolution alone. Different regions also recover at different speeds because climate itself is never uniform. Monsoon systems across Asia respond differently to volcanic cooling than rainfall patterns in eastern Africa. Some areas become drier, while others experience altered seasonal timing rather than dramatic reductions in precipitation. Ocean currents continue redistributing heat around the globe, moderating temperatures in coastal environments even as inland regions cool more sharply. These regional differences complicate every attempt to reconstruct the eruption's consequences. One scientist studying lake sediments in East Africa may conclude that environmental disruption is relatively modest. Another examining pollen records from South Asia may find evidence of profound ecological change. A third analyzing marine cores from the Indian Ocean observes still another pattern. None of these researchers is necessarily wrong. They are simply examining different pieces of an exceptionally complex planetary response. The same complexity almost certainly characterizes human experience. A child growing up along a productive coastline may remember difficult years but never face starvation. Another born inland could experience repeated shortages that reshape every aspect of daily life. Communities separated by only a few hundred kilometers may develop entirely different traditions because their environments demand different solutions. This diversity of experience also helps explain why no single archaeological or genetic record captures the whole story. Humanity does not survive because every group succeeds. It survives because enough groups succeed. Some disappear without descendants, others retreat into isolated refuges. A few expand into newly favorable landscapes as conditions improve. Their histories intertwine across thousands of years until later migrations reconnect. Populations that had once been separated by geography and environmental change. Looking across this ancient world, the eruption appears less like a single moment frozen in time, and more like a vast ripple spreading outward through landscapes already shaped by Ice Age climates. The wave strikes different shores with different force, leaving behind not one universal outcome but countless local stories of adaptation, loss, recovery, and endurance. Together, those scattered stories preserve the fragile thread that allows humanity to continue its long journey into the future. Humanity is not alone in this ancient world. Long before cities, kingdoms, or written history, several different kinds of humans share the planet, each shaped by hundreds of thousands of years of evolution in different environments. To look across Eurasia 74,000 years ago is not to see a single species marching inevitably toward global dominance. It is to see a family of closely related human populations, each following its own evolutionary path, each remarkably successful in its own homeland, and each facing the same changing Earth in different ways. In Western Europe and much of Western Asia, the landscape belongs primarily to the Neanderthals. They have lived there for hundreds of thousands of years, surviving repeated Ice Age cycles that would challenge almost any large mammal. Their bodies reflect those demanding environments. They're generally shorter and more powerfully built than contemporary Homo sapiens, with broad chests, strong limbs, and facial features that help warm cold air before it reaches the lungs. For generations, Neanderthals are misunderstood. Early archaeological discoveries portray them as primitive, intellectually limited, and destined to disappear before the arrival of modern humans. That image begins to change dramatically during the late 20th and early 21st centuries. Excavations reveal carefully manufactured stone tools, controlled use of fire, sophisticated hunting strategies, and evidence that they care for injured members of their communities, long after serious wounds would have prevented independent survival. Ancient DNA transforms the picture even further. The sequencing of the Neanderthal genome demonstrates beyond doubt that they interbreed with Homo sapiens after the two populations encounter one another. Their disappearance is therefore not a simple story of replacement. Part of the Neanderthal legacy survives within billions of living people today. At the time of the Toba eruption, however, these encounters have probably not yet become widespread. Neanderthals continue occupying much of Europe and Western Asia, while Homo sapiens remains concentrated primarily in Africa and parts of Southern Asia. The two populations exist largely in separate worlds, connected only by immense distances and changing climates. Farther east lives another mysterious branch of humanity. The Denisovans remain among the greatest surprises in modern paleoanthropology. Their existence comes to light only in the early 21st century, when researchers extract DNA from a tiny finger bone and several teeth recovered from Denisova Cave in Siberia. The fossils themselves reveal remarkably little. Without genetic analysis, scientists might never have realized they belonged to an entirely distinct human population. The DNA tells an extraordinary story. Denisovans are close relatives of Neanderthals, but genetically distinct. They also interbreed with Homo sapiens, leaving measurable genetic contributions among modern populations in New Guinea, Australia, parts of Southeast Asia, and portions of East Asia. Yet despite these discoveries, almost everything else about them remains uncertain. No complete Denisovan skeleton has been found. Researchers still debate their physical appearance, geographic distribution, and cultural diversity. They may occupy enormous portions of Eastern Asia, adapting to habitats ranging from Siberian mountains to tropical islands. The evidence remains incomplete, and every new fossil has the potential to reshape current understanding. Somewhere across island Southeast Asia, another remarkable human species survives. Homo floresiensis, often nicknamed the Hobbit because of its small stature, inhabits the Indonesian island of Flores. Adults stand only about 1 meter tall, yet manufacture stone tools and hunt surprisingly large animals. Whether they descend from much earlier human ancestors or represent an isolated offshoot of another population remains actively debated. Their presence illustrates an important point. Human evolution does not produce a single linear progression from primitive to advanced forms. Instead, multiple experiments unfold simultaneously across different environments. Isolation, climate, geography, and available resources shape each population in unique ways. Exactly how the Toba eruption affects these various human groups remains one of the most intriguing unanswered questions in prehistoric research. For Neanderthals living thousands of kilometers away in Europe, the immediate effects may be relatively modest compared with populations nearer the eruption. Climatic fluctuations already characterize their world. They possess extensive experience adapting to cold environments, shifting animal migrations, and changing vegetation. Even so, additional environmental stress could still influence prey availability and regional ecosystems. Large herbivores such as mammoths, bison, horses, and reindeer form essential components of Neanderthal hunting economies. Alterations in climate or vegetation need not eliminate these animals entirely to create serious challenges. Changes in migration timing or herd distribution alone can force hunters to adjust strategies refined over countless generations. Denisovan populations may experience very different conditions depending upon where they actually live. If some inhabit regions of Eastern Asia affected by volcanic ash or altered monsoon systems, they could face environmental disruptions comparable to those confronting Homo sapiens farther south. If others occupy more distant environments, their experience might differ substantially. Unfortunately, the archaeological record remains too fragmentary to answer these questions with confidence. The same uncertainty surrounds Homo floresiensis. Flores lies within the Indonesian archipelago relatively close to Toba compared with Africa or Europe. Yet island geography complicates every prediction. Ocean currents, prevailing winds, volcanic ash distribution, and local ecological conditions all influence survival. Scholars still debate precisely when Homo floresiensis disappears, and no direct evidence links its extinction to the Toba eruption. This broader perspective reveals something profound about evolution. Natural disasters rarely select winners and losers according to intelligence alone. Success depends upon an intricate combination of environmental circumstances, population size, genetic diversity, mobility, cultural flexibility, and simple chance. A small community occupying a favorable refuge may survive, while a larger population elsewhere disappears. Geographic luck can matter as much as biological adaptation. Homo sapiens appears especially effective at exploiting diverse habitats. By this period, modern humans occupy forests, grasslands, river valleys, coastlines, and increasingly varied ecological settings. Such diversity reduces dependence upon any single environment. If one habitat becomes temporarily unfavorable, others may continue supporting scattered populations. This does not guarantee long-term success. The archaeological evidence indicates that Homo sapiens itself experiences repeated local disappearances throughout prehistory. Groups migrate, merge, fragment, and occasionally vanish altogether. Evolution proceeds not through uninterrupted expansion, but through countless episodes of contraction and recovery. Another important factor distinguishes modern humans from many earlier populations. Social networks appear increasingly extensive. Stone materials sometimes travel considerable distances from their geological sources, suggesting either long-range mobility or exchange between neighboring groups. Similar symbolic objects emerge across surprisingly broad regions. Although the exact nature of these connections remains debated, they imply that information materials and perhaps even people occasionally move across landscapes larger than those occupied by individual communities. Such networks provide resilience. If one group encounters environmental hardship, neighboring populations may preserve cultural knowledge, technological innovations, or genetic diversity that later contribute to recovery. Isolation can protect communities from certain dangers, but complete isolation also limits opportunities for renewal. Looking back from the present, it is tempting to focus only on Homo sapiens because ours is the only surviving human species. Yet 74,000 years ago, that outcome remains far from certain. Neanderthals continue thriving across much of Eurasia. Denisovans occupy mysterious territories still largely hidden from science. Island populations follow their own unique evolutionary journeys. Modern humans represent just one branch of a remarkably diverse human family. The Toba eruption unfolds against this crowded evolutionary landscape, influencing multiple human lineages whose stories intersect in ways researchers are only beginning to understand. Some will disappear. Some will contribute genes to future populations before fading from the fossil record. One lineage will eventually spread across every continent, carrying within its genome faint echoes of all the others. At this moment, however, no observer could possibly know which branch of humanity will inherit the future. The ancient world remains full of possibilities balanced delicately between survival and disappearance, with every generation living under skies still slowly recovering from one of the greatest volcanic eruptions Earth has ever known. The most important inventions in human history are not always the ones that leave obvious archaeological traces. Stone spear points survive for tens of thousands of years. Bones preserve the marks of carefully butchered animals. Hearths leave thin layers of charcoal buried beneath ancient cave floors. Yet many of the innovations that may have mattered most during periods of environmental crisis vanish almost completely. A new way of organizing a hunt, a more efficient method of sharing food, a different pattern of seasonal movement, or a stronger bond between neighboring communities rarely fossilizes. Their influence survives only indirectly reflected in the continued existence of the people who practiced them. Periods of prolonged environmental instability often reward flexibility over specialization. Animals that depend upon a single habitat or one particular food source become increasingly vulnerable when conditions change. Humans possess an unusual advantage. They are specialists in adaptation itself. Rather than evolving a body perfectly suited to one environment, Homo sapiens develops an extraordinary capacity to modify behavior as circumstances demand. This difference may appear subtle, but it changes everything. Consider a hunting strategy refined over generations. A community learns where herds usually cross a river during the dry season. Young hunters memorize hidden paths through woodland that allow them to approach unseen. Older members recognize the tracks of pregnant females, injured animals, and dominant males. Such knowledge accumulates slowly through observation and experience. Then the environment changes. Rain arrives later than expected. Grasslands shrink. The herds alter their migration routes. Every lesson passed from grandparents to grandchildren suddenly becomes less reliable. A rigid society might continue following familiar patterns until failure becomes unavoidable. A flexible one experiments. It explores unfamiliar valleys, hunts different prey, and revises traditions without abandoning the knowledge that still proves useful. This capacity for continual adjustment becomes one of humanity's defining strengths. Archaeologists often describe the Late Stone Age as a period of growing technological sophistication. Yet sophistication does not necessarily mean complexity in the modern sense. Many improvements involve small refinements rather than dramatic inventions. Stone blades become thinner, sharper, and more standardized. Different tool shapes appear suited to particular tasks such as scraping hides, cutting plants, woodworking, or processing bone. Each refinement saves energy, reduces waste, or increases efficiency by only a modest amount. Across thousands of years, those modest improvements accumulate. A slightly sharper cutting edge allows hunters to process carcasses more quickly before predators arrive. Better hide-working tools produce warmer clothing and more durable shelters. Improved spear points increase hunting success, even by a small percentage, providing additional food during difficult seasons. Evolution frequently rewards countless incremental advantages rather than spectacular breakthroughs. Fire continues to occupy a central place within this adaptive system. Its importance extends far beyond warmth and cooking. Fire transforms landscapes. Controlled burning encourages the growth of fresh vegetation attractive to grazing animals. Dense undergrowth becomes easier to cross. Dangerous predators lose some of their concealment. Certain edible plants regenerate more successfully after low-intensity fires. Although the exact extent of deliberate landscape burning during this period remains debated, evidence from later hunter-gatherer societies demonstrates that fire can become a sophisticated environmental management tool rather than merely a source of heat. Cooking itself represents one of humanity's quiet revolutions. Raw meat demands prolonged chewing and digestion. Many roots remain indigestible without heating. Certain toxins found in wild plants break down only after careful preparation. Cooked food delivers calories more efficiently, while reducing disease risks associated with parasites and harmful bacteria. During times of scarcity, the ability to extract maximum nutrition from available resources becomes increasingly valuable. Food storage also begins assuming greater importance. Direct archaeological evidence remains limited because baskets, wooden containers, and leather bags rarely survive. Nevertheless, anthropological comparisons suggest that many hunter-gatherer societies preserve food whenever environmental conditions permit. Smoked meat lasts longer than fresh meat. Dried fish can sustain families through lean periods. Edible nuts and seeds often remain usable for months if protected from moisture. Such practices reduce dependence upon immediate hunting success. Knowledge itself becomes another essential resource. Unlike instinctive animal behavior, human survival depends heavily upon learned information. Children spend years acquiring skills from experienced adults. They learn which plants nourish and which poison. They recognize seasonal changes, weather patterns, animal behavior, and safe water sources. During periods of environmental disruption, this educational process becomes even more significant because familiar conditions no longer provide reliable guidance. Older members of the community assume particular importance. In purely physical terms, an elderly hunter may contribute less directly than a younger adult. Yet accumulated experience often compensates for declining strength. Long memories preserve knowledge of rare droughts, unusual migrations, distant waterholes, and alternative food sources encountered decades earlier. Anthropologists studying traditional societies frequently observe that older individuals provide critical decision-making during environmental crises precisely because they remember events beyond the experience of younger generations. Language amplifies this advantage enormously. Complex communication allows humans to describe places not currently visible dangers encountered elsewhere and solutions discovered by neighboring groups. Unlike many animals that learn primarily through direct observation, people transmit abstract information across both space and time. A child can prepare for a drought never personally experienced because someone else remembers it. Although spoken language leaves no fossils, many researchers believe its increasing sophistication plays a decisive role in the success of Homo sapiens. Social organization evolves alongside technology. Small family groups rarely survive indefinitely in complete isolation. Marriage exchanges, seasonal gatherings, and cooperative hunting create broader social networks, connecting otherwise separate communities. These relationships provide practical advantages extending well beyond companionship. If one group experiences poor hunting, relatives elsewhere may offer temporary assistance. If disease strikes a local community, survivors can join neighboring populations rather than disappearing entirely. If environmental change renders one territory temporarily uninhabitable, existing social connections facilitate movement into new areas. Modern hunter-gatherer societies frequently maintain such flexible networks, despite occupying enormous territories. While direct comparison with late Pleistocene populations requires caution, similar patterns likely enhance resilience among early Homo sapiens. Symbolic behavior may also strengthen social cohesion. Archaeological discoveries from sites such as Blombos Cave reveal engraved pieces of ochre, carefully shaped bone tools, and shell beads dating to approximately this period. Scholars continue debating their precise meanings, but they almost certainly reflect capacities extending beyond immediate survival. Personal ornaments communicate identity. Decorated objects reinforce shared traditions. Repeated symbolic practices strengthen group cohesion. Communities that trust one another cooperate more effectively during hardship than collections of unrelated individuals acting independently. Even music may play a role, though direct evidence remains extremely limited. Rhythmic movement, coordinated work, and shared vocalization help synchronize group activities in many human societies. Such behaviors encourage cooperation, reduce conflict, and reinforce collective identity. Organic musical instruments rarely survive from such remote periods, but the cognitive capacity underlying music almost certainly predates recorded history. None of these developments guarantees survival on its own. Sharper tools cannot overcome complete ecological collapse. Better communication cannot create food where none exists. Stronger social networks cannot eliminate drought or volcanic winter. Together, however, they create remarkable resilience. Humanity's greatest adaptation is not a particular invention, but an entire way of responding to uncertainty. Faced with unfamiliar environments, people observe, experiment, remember successful strategies, discard failed ones, and teach the next generation what they have learned. This continuous cultural evolution operates far more rapidly than biological evolution, allowing Homo sapiens to adjust within years rather than millennia. If the Toba eruption places extraordinary pressure upon early human populations, these quiet innovations may prove just as significant as favorable geography or fortunate climate. Survival belongs not simply to those who escape disaster, but to those capable of transforming knowledge into adaptation before changing conditions overwhelm them. Across countless forgotten camps scattered through Africa and Asia, around fires whose ashes now lie buried beneath thousands of years of sediment, those transformations continue almost unnoticed. No monument records them, no inscription celebrates them. Yet they gradually shape a species increasingly prepared to face an unpredictable world, one small improvement at a time. The greatest legacy of the Toba eruption may not be found beneath the waters of Lake Toba or inside layers of volcanic ash scattered across Asia. It may instead be reflected in the extraordinary journey that follows. Within a few tens of thousands of years after the eruption, Homo sapiens expands farther and faster than any previous human species, reaching environments that earlier populations either never entered or occupied only briefly. Whether the eruption directly shapes this expansion, or simply occurs before it remains an open question, but the world that emerges afterward is one in which modern humans become increasingly difficult to stop. The transformation is gradual rather than sudden. There is no single migration that carries humanity across the globe. Instead, countless small movements accumulate over thousands of generations. One family follows a river farther than their parents ever travelled. Another crosses a mountain pass during an unusually favourable season. A coastal group continues along unfamiliar shorelines in search of shellfish and fresh water. None of these journeys appears historically significant in isolation. Together they redraw the map of the human world. Africa remains the centre of this story. Far from being merely the place where Homo sapiens first evolves, the continent continues serving as a reservoir of genetic diversity and cultural innovation long after our species appears. Populations remain distributed across forests, savannas, deserts, highlands and coastlines, each adapting to local conditions while occasionally reconnecting with neighbouring groups. These repeated episodes of separation and reunion preserve diversity even during periods of environmental stress. Eventually, some of these populations begin expanding beyond Africa in larger numbers. Exactly when this movement becomes widespread remains debated, but most evidence suggests that major dispersals occur after the approximate period of the Toba eruption. Small groups travel through northeastern Africa into the Arabian Peninsula, following coastlines, river systems, and ecological corridors opened by changing climates. Their progress is rarely continuous. Populations pause for generations in favourable regions before moving again as opportunities arise. The Arabian Peninsula itself looks very different from the harsh deserts familiar today. Climate fluctuates repeatedly during the late Pleistocene. At certain times, increased rainfall transforms large areas into grasslands dotted with lakes and rivers. These greener landscapes provide pathways for animals and humans alike. Archaeological discoveries of ancient lake beds, fossilized river channels, and stone tools reveal that regions now dominated by sand once supported thriving ecosystems. As humans spread eastward, they encounter a mosaic of environments. Some follow the southern coastline of Asia, exploiting marine resources remarkably similar to those already familiar from African shores. Others move inland along river valleys, where freshwater vegetation and game animals remain abundant. The pace of expansion depends less upon ambition than upon ecology. Populations move when resources allow and remain stationary when conditions become difficult. This flexibility produces one of the defining characteristics of Homo sapiens. Unlike earlier human populations that often appear closely associated with particular environments, modern humans repeatedly demonstrate an ability to occupy entirely new ecological settings. Dense tropical forests, temperate woodlands, open grasslands, and rugged mountains all become part of the expanding human landscape. The evidence for this expansion appears in surprising places. Stone tools discovered across Arabia suggest repeated occupations during favorable climatic intervals. Archaeological sites in India reveal continued human presence despite environmental fluctuations. Fossils and artifacts in Southeast Asia indicate that Homo sapiens reaches island environments, requiring at least short crossings of open water. Even relatively modest sea journeys demand planning, cooperation, and confidence in exploring unfamiliar territory. Perhaps the most remarkable destination lies farther still. At some point, modern humans arrive in Sahul, the prehistoric landmass connecting Australia and New Guinea, during periods of lower sea level. Even though sea levels are substantially reduced, complete overland travel remains impossible. Reaching Sahul requires crossing stretches of open ocean that are visible from shore in some places, but still demand intentional watercraft or floating platforms. The significance of this achievement is difficult to overstate. Crossing open water demonstrates more than technological competence. It reflects the willingness to enter environments from which immediate return may not be possible. Such voyages require planning, social coordination, and confidence that unknown lands beyond the horizon might support life. These characteristics become hallmarks of later human expansion. As climates continue fluctuating through the Ice Age, people repeatedly adjust migration routes rather than abandoning movement altogether. Glaciers block northern landscapes before eventually retreating. Sea levels rise and fall, alternately exposing and drowning coastal corridors. Rivers change course, forests expand and contract. Humanity responds not by remaining fixed, but by continually reshaping its relationship with geography. The archaeological record increasingly reveals this adaptability. Different tool traditions emerge across Eurasia, reflecting local environments rather than universal cultural patterns. Hunting equipment evolves alongside available prey. Shelter construction varies according to climate. Clothing, though rarely preserved, almost certainly becomes increasingly sophisticated in colder regions. Innovation spreads through social networks while continuing to diversify locally. Genetic evidence mirrors these archaeological patterns. As populations expand into new territories, they carry only portions of Africa's original genetic diversity. Each migration represents a kind of biological sampling event. Small founding populations establish themselves in distant regions before gradually increasing in number. Subsequent isolation allows subtle genetic differences to accumulate, while occasional contact between neighboring populations introduces fresh diversity. This process explains why genetic variation generally decreases with increasing distance from Africa. It does not imply superiority or inferiority among populations. Rather, it reflects the sequence of migrations undertaken by relatively small groups over thousands of years. Every community carries the imprint of countless ancestral journeys extending back to the African homeland. Environmental adaptation also becomes increasingly visible. Populations living in northern latitudes gradually evolve lighter skin pigmentation that improves vitamin D production under reduced sunlight. Communities occupying the Tibetan Plateau develop genetic changes supporting life at high altitude. Arctic populations acquire metabolic adaptations suited to diets rich in marine mammals and fish. These changes occur long after the Toba eruption, yet they illustrate the continuing partnership between biological evolution and cultural flexibility. Scholars still debate whether the eruption itself accelerates any of these broader processes. Some argue that surviving environmental stress favors behavioral adaptability, encouraging mobility and innovation. Others contend that the expansion of Homo sapiens follows trajectories already established, before Toba driven primarily by long-term climatic opportunities rather than volcanic catastrophe. The evidence remains incomplete. No single explanation fully accounts for the remarkable success of Homo sapiens during the late Pleistocene. Climate geography, technology, cooperation, demographic growth and chance all contribute in ways that are difficult to separate. Evolution rarely depends upon one decisive event. More often it reflects countless interacting influences unfolding across immense spans of time. Even so, the symbolism remains powerful. Whether or not Toba nearly extinguishes humanity, it reminds us that our species does not emerge into a stable world waiting to be conquered. Instead, Homo sapiens grows within a planet defined by constant change. Volcanoes erupt, glaciers advance, deserts expand, coastlines disappear beneath rising seas. Every generation inherits landscapes different from those known by its ancestors. Perhaps that continual encounter with change becomes humanity's greatest teacher. Rather than mastering nature early, humans learn to move with it, adapting again and again as environments shift beneath their feet. Those lessons accumulated across thousands of forgotten lives eventually carry our species beyond Africa, across oceans into frozen northern plains, and ultimately to nearly every corner of the Earth. The journey that follows the ancient eruption is therefore more than a migration across continents. It is the gradual emergence of a species whose defining characteristic is not physical strength or perfect adaptation to any single habitat, but an extraordinary capacity to keep moving forward even when the world itself refuses to remain the same. As the story of the Toba eruption reaches modern audiences, it often becomes larger than the evidence itself. Few prehistoric events have inspired as many dramatic headlines. Some describe the eruption as the moment humanity nearly vanished forever. Others dismiss it entirely, arguing that it left a little lasting mark on human evolution. Between those extremes lies a far more interesting reality, one in which careful science slowly untangles a mystery assembled from rocks, fossils, genes, climate records, and archaeological discoveries scattered across half the planet. The attraction of simple explanations is understandable. History often seems easier to comprehend when one event appears to cause one outcome. A great battle ends an empire, a plague transforms medieval Europe, a meteorite contributes to the extinction of the non-avian dinosaurs. These narratives provide satisfying clarity, even though the deeper reality usually involves many interacting causes unfolding over long periods. The Toba eruption invites the same temptation. It is after all one of the largest volcanic events known from the recent geological past. Modern humans exist at the time. Genetic evidence suggests relatively small ancestral populations. The pieces seem ready to fit together into a single dramatic conclusion. Yet nature rarely arranges its evidence so neatly. One common misconception is that the eruption instantly plunges the entire planet into decades of darkness. This image owes much to comparisons with fictional apocalyptic scenarios where sunlight disappears almost completely and ecosystems collapse everywhere at once. The geological evidence does not support such a universal picture. Ash falls unevenly. Atmospheric circulation distributes volcanic aerosols differently across regions. Oceans moderate temperature changes in coastal environments. Some ecosystems experience severe disruption, while others remain comparatively resilient. Even during major climatic disturbances, the Earth continues functioning as a remarkably complex system, rather than responding with perfect uniformity. Another popular belief suggests that humanity is reduced to only a handful of surviving individuals. This claim usually arises from misunderstanding genetic terminology. As discussed earlier, effective population size differs substantially from the total number of living people. A genetically small population does not necessarily mean only a few thousand humans remain alive. It reflects how genetic diversity passes from one generation to the next, influenced by reproduction, migration, isolation, and demographic structure over long periods. Similarly, genetic bottlenecks themselves are often misunderstood. A bottleneck does not always represent a sudden catastrophe. It can develop gradually as populations remain fragmented for thousands of years. Repeated local extinctions, changing climates, and shifting migration patterns may all contribute without any single event becoming solely responsible. This distinction becomes particularly important when discussing toba. Modern genetics strongly suggests that Homo sapiens experiences periods of reduced ancestral diversity. What remains uncertain is exactly how much of that pattern results directly from the eruption, and how much reflects broader evolutionary processes already underway. Popular culture sometimes moves in the opposite direction by dismissing the eruption almost completely. Because archaeological sites in India preserve evidence of continued human occupation, some conclude that toba has little meaningful effect at all. This interpretation oversimplifies the evidence in a different way. Environmental disasters need not eliminate entire populations to influence evolutionary history. Repeated food shortages may reduce birth rates. Communities may fragment into smaller groups. Migration routes may shift permanently. Competition for resources may intensify. Local extinctions may occur even while neighboring populations survive. Each of these processes leaves subtle marks rather than dramatic ones, yet together they can reshape the future of a species. Another enduring misconception involves the volcano itself. Illustrations often portray toba as an ordinary cone-shaped mountain exploding spectacularly into the sky. In reality, supervolcanoes behave very differently. Rather than constructing steep volcanic cones like Mount Fuji or Mount St. Helens, they often consist of enormous magma systems spread beneath broad landscapes. After major eruptions, the ground above the emptied chamber collapses inward, producing vast calderas many kilometers across. Today's Lake Toba occupies exactly such a collapsed structure. Visitors standing beside the lake may struggle to recognize that they are looking not at a typical volcanic crater, but at the remains of one of Earth's greatest eruptions. The peaceful scenery itself becomes misleading. Calm water reflects surrounding hills. Fishing boats move quietly across the surface. Villages occupy fertile slopes enriched by ancient volcanic deposits. Without geological knowledge, almost nothing suggests the unimaginable violence that once transformed the landscape. The scientific process responsible for uncovering this history is equally remarkable. No single researcher solves the mystery. Instead, volcanologists analyze ash chemistry. Geneticists reconstruct ancestral populations. Archaeologists excavate ancient campsites. Climate scientists build computer simulations. Geochemists study microscopic minerals trapped within volcanic deposits. Paleoecologists examine fossil pollen preserved in lake sediments. Each discipline contributes only part of the answer. When these separate strands are woven together, an increasingly detailed picture begins to emerge. Even disagreements play a constructive role. Competing hypotheses encourage new fieldwork. Improved dating techniques reduce chronological uncertainty. More sophisticated climate models test earlier assumptions. Fresh fossil discoveries challenge long-standing interpretations. Science advances not because everyone immediately agrees, but because disagreement motivates better evidence. The Toba debate provides one of the clearest examples of this process. Early catastrophe models emphasize extreme climatic cooling. Later studies revise those estimates. New archaeological discoveries complicate earlier demographic scenarios. Genomic analyses introduce entirely new perspectives unavailable only a generation ago. Each revision produces a narrative that is simultaneously less dramatic in some respects and far richer in others. Perhaps the greatest misconception concerns certainty itself. People often expect science to deliver final answers. Instead, scientific understanding evolves continuously. New technologies recover ancient proteins from fossils once considered useless. Satellite imagery reveals forgotten river systems beneath deserts. Improved dating methods narrow age estimates by thousands of years. Entire human populations such as the Denisovans become known through fragments that would once have seemed insignificant. Every advance changes the questions researchers ask. This does not indicate weakness. Quite the opposite. A willingness to revise conclusions when new evidence appears represents one of science's greatest strengths. The story of Toba today differs from the story told 30 years ago because researchers know far more than they once did. It will almost certainly continue changing as future discoveries emerge. Some of the most exciting evidence may still lie hidden. Ancient coastlines submerged beneath rising seas may preserve archaeological sites untouched for tens of thousands of years. Lake sediments not yet drilled may contain more complete environmental records. Undiscovered fossils may reveal where Denisovans actually lived. Future genetic methods may reconstruct demographic histories with unprecedented precision. The mystery remains unfinished. Perhaps that incompleteness explains why the Toba eruption continues capturing imagination so powerfully. It occupies the narrow boundary between certainty and mystery. The eruption itself unquestionably occurs. Its extraordinary scale is beyond dispute. Its influence upon climate is well supported. Its exact role in shaping human evolution, however, remains one of the most fascinating scientific debates still unfolding. Rather than diminishing the story, this uncertainty enriches it. The ancient volcano does not offer a simple moral or a single dramatic turning point. Instead, it reminds us that history, especially prehistory, is rarely written in straight lines. It is assembled gradually from scattered fragments, each preserving only part of a much larger picture. The closer scientists examine those fragments, the more remarkable that larger picture becomes, revealing a humanity whose greatest achievement may not have been avoiding catastrophe altogether, but learning to endure a world where certainty is always in short supply. The Toba eruption stands among a long succession of geological upheavals that have repeatedly reshaped life on Earth. Looking only at the volcano itself risks missing its broader significance. It is not an isolated anomaly, but one chapter in a planet whose history is written through continual transformation. Continents drift across the globe. Oceans open and disappear. Mountains rise only to erode away. Ice sheets advance over entire landscapes before retreating again. Volcanoes erupt. Meteorites strike rivers, change course, and deserts replace forests that once stretched to distant horizons. The Earth has never been still. Life evolves within that restless world rather than despite it. Every species alive today carries the imprint of ancient environmental change. Forests expanding during warmer climates encourage one set of adaptations. Cooling temperatures reward another. Rising sea levels isolate populations on islands where evolution follows unexpected paths. Falling sea levels reconnect continents, allowing migrations that were previously impossible. The human story is therefore inseparable from geology. Long before our ancestors learned to shape metal or cultivate crops, they're already responding to shifting climates driven by forces far beyond human control. The Toba eruption represents one of those forces dramatic enough to capture attention, even among countless other environmental changes unfolding across the late Pleistocene. It is not the first catastrophe to influence evolution. Roughly 66 million years before the Toba eruption, a massive asteroid strikes what is now the Yucatan Peninsula. The impact triggers global wildfires, enormous tsunamis, and prolonged climatic disruption. The extinction of the non-avian dinosaurs follows opening ecological opportunities that eventually allow mammals to diversify in extraordinary ways. Without that ancient impact, the evolutionary pathway leading toward Homo sapiens might never exist. Yet even this famous event is only one part of a much longer history. Around 252 million years ago, at the boundary between the Permian and Triassic periods, Earth experiences the greatest mass extinction known. Enormous volcanic eruptions associated with the Siberian traps release vast quantities of carbon dioxide and other gases over extended periods. Oceans lose oxygen. Global temperatures rise dramatically. Approximately 90% of marine species disappear. Unlike the relatively brief eruption at Toba, these volcanic episodes continue for hundreds of thousands of years. Their effects illustrate another way geology can transform biology, not through sudden catastrophe alone, but through persistent environmental pressure, reshaping ecosystems generation after generation. Other super-eruptions punctuate Earth's history as well. Yellowstone in North America has produced several enormous eruptions over the past 2 million years. Taupo in New Zealand has generated exceptionally powerful volcanic events. Campi Flegrei near modern Naples remains an active volcanic system capable of significant future eruptions, although nothing indicates an eruption comparable to Toba is imminent. Each reminds us that supervolcanoes belong to Earth's natural geological processes, rather than ancient curiosities that no longer matter. Fortunately, they remain extraordinarily rare. The intervals separating major super-eruptions generally span hundreds of thousands of years or longer. Humanity has never experienced one during recorded history. Modern civilization has therefore developed under unusually stable geological conditions, compared with much of Earth's deeper past. Climate change also unfolds repeatedly throughout the ice ages without requiring volcanic triggers. Glacial cycles, driven largely by subtle variations in Earth's orbit, alter temperatures, rainfall, and sea levels across the globe. During colder periods, enormous ice sheets spread across northern Europe and North America. Sea levels fall by more than 100 meters, exposing land bridges connecting regions now separated by water. The Bering Land Bridge eventually allows humans to enter the Americas. The Sunda Shelf connects many islands of Southeast Asia into larger continuous landscapes. The Sahara alternates between arid desert and greener environments, supporting lakes, rivers, and abundant wildlife. These transformations occur over thousands of years, yet their consequences rival those of many sudden catastrophes. The Toba eruption intersects with this already dynamic climatic background. Rather than acting upon a stable world, it strikes a planet accustomed to continual change. This distinction matters because ecosystems already possess varying degrees of resilience. Species surviving repeated glacial fluctuations may respond differently to volcanic cooling than they would under otherwise stable climatic conditions. Human adaptability likewise develops within this broader context. Our ancestors do not suddenly become flexible because one volcano erupts. Instead, flexibility itself evolves gradually through countless encounters with changing environments. Droughts encourage new migration routes. Expanding grasslands alter hunting strategies. Rising seas reshape coastlines. Volcanic eruptions become one challenge among many within an endlessly shifting world. Geological records preserve fascinating evidence of these repeated transformations. Lake sediments capture changing pollen communities as forests expand and contract. Cave formations record ancient rainfall patterns through subtle chemical variations. Coral reefs reveal past sea levels. Ice cores preserve atmospheric composition extending back hundreds of thousands of years. Together, these archives demonstrate that environmental stability is often the exception rather than the rule. One striking lesson emerges repeatedly. Species that survive long periods tend to possess some capacity for adjustment. This does not guarantee permanence. The fossil record contains countless examples of highly successful organisms eventually disappearing when conditions exceed their adaptive limits. The giant ground sloths vanish. The woolly mammoths disappear. Saber-toothed cats leave only fossils. Entire branches of the human family fade into extinction. Longevity in evolutionary terms depends not upon invincibility, but upon continually responding to changing circumstances. Homo sapiens appears especially effective at this process. Our species occupies tropical forests without losing the ability to survive Arctic winters. It crosses deserts, mountains, oceans, and grasslands while developing distinct cultural solutions to local challenges. Technology extends biological capabilities rather than replacing them. Knowledge accumulates across generations instead of beginning anew each lifetime. The eruption at Toba therefore becomes symbolic of something larger than itself. Whether or not it nearly reduces humanity to extinction, it represents the type of environmental upheaval that repeatedly tests the limits of adaptation. The survivors inherit not merely altered landscapes, but opportunities to refine behaviors that continue serving future generations long after volcanic ash disappears. Modern Earth remains geologically active. Thousands of volcanoes continue operating worldwide. Earthquakes reshape coastlines. New islands emerge while others slowly erode beneath rising seas. The processes responsible for Toba have never ceased. They simply operate according to timescales that often exceed individual human lifetimes. Looking across deep time changes perspective, human civilization, impressive though it is, occupies only the briefest moment within Earth's geological history. Agriculture appears yesterday. Writing emerges moments later. Modern industry belongs almost entirely to the present instant. The volcano beneath Lake Toba, by contrast, develops through hundreds of thousands of years before erupting over the course of days. This difference in timescale is humbling. It reminds us that the landscapes we often regard as permanent are temporary expressions of ongoing geological change. Mountains become valleys. Lakes replace volcanic craters. Coastlines migrate with changing seas. Forests grow where ash once buried everything beneath silent grey horizons. The Earth continually rebuilds itself. The ancient eruption survives today not because the landscape remains frozen in catastrophe, but because careful scientific investigation uncovers traces preserved within rocks, sediments, and living genomes. Those traces reveal a planet where destruction and renewal are inseparable processes, each preparing the conditions from which the next chapter of life's story eventually emerges. Today, the waters of Lake Toba appear almost impossibly calm. Early morning mist drifts across the surface before sunlight breaks through the surrounding hills. Fishing boats leave gentle ripples that disappear almost as quickly as they form. Villages overlook fertile slopes where crops grow in volcanic soil, enriched over countless generations. Visitors arrive seeking cool mountain air, scenic landscapes, and quiet shorelines. Few places seem less connected to global catastrophe, yet beneath that peaceful surface lies one of the greatest geological scars on Earth. The lake stretches for nearly 100 kilometers, filling an immense caldera created when the volcanic roof collapsed into the emptied magma chamber below. The surrounding cliffs and ridges are not merely picturesque mountains. They are fragments of a landscape violently rearranged during an eruption that dispersed ash across continents and entered the evolutionary story of our own species. Modern scientists continue returning to this remarkable place, because every new investigation reveals another fragment of its history. Geologists collect volcanic rocks measuring tiny crystals that preserve chemical evidence of magma formation deep within the Earth's crust. These minerals function almost like microscopic clocks, allowing researchers to reconstruct the sequence of events leading to the eruption. Advances in radiometric dating steadily improve estimates of its timing, narrowing uncertainties that once spanned several thousand years. Lake sediments provide another invaluable archive. Year after year, fine particles settle quietly onto the lake floor building, an uninterrupted record of environmental change. By drilling deep into these sediments, researchers recover cores containing pollen, volcanic ash, microscopic organisms and chemical signatures stretching back through tens of thousands of years. Layer by layer, these cores reveal how ecosystems recover after catastrophe, how climates fluctuate naturally, and how volcanic landscapes gradually become thriving habitats once again. Around the world, similar scientific efforts continue expanding the story. Improved satellite imaging reveals ancient river systems now buried beneath deserts. Underwater archaeology begins exploring coastlines that existed during periods of lower sea level, searching for traces of prehistoric communities now hidden beneath the ocean. Ancient DNA laboratories recover increasingly complete genomes from fossils once thought incapable of preserving genetic material. Climate models incorporate more sophisticated atmospheric physics than those available only a generation ago. Each technological advance changes the questions researchers can ask. Instead of debating only whether the Toba eruption caused a human bottleneck, scientists now examine how different populations responded, according to geography, ecology, and existing social networks. Rather than viewing prehistoric humans as passive victims of environmental change, researchers increasingly recognize them as remarkably adaptable communities capable of exploiting diverse landscapes under extraordinarily difficult conditions. This shift reflects a broader transformation within archaeology and anthropology. Earlier generations often searched for single causes explaining major historical events. Today, scholars more commonly recognize that multiple processes usually operate simultaneously. Climate influences migration, but so do social relationships. Geological disasters alter environments, yet cultural innovation shapes how people respond. Genetics records demographic changes, while archaeology reveals behavioral flexibility. None of these perspectives alone tells the complete story. The Toba eruption illustrates this beautifully. The volcano unquestionably erupts with astonishing force. The atmosphere undoubtedly changes. Regional ecosystems experience profound disruption. Human populations almost certainly face serious environmental challenges. Beyond these broad conclusions, however, certainty gives way to careful interpretation. How severe is the climatic cooling? Which regions experience the greatest ecological stress? How many human populations survive continuously? How important are coastal refuges? To what extent do migrations reshape genetic diversity? Each question remains an active area of research rather than a closed chapter. Far from diminishing the significance of the eruption, this ongoing uncertainty makes it scientifically richer. The story continues evolving because new evidence continues appearing. Perhaps submerged archaeological sites along ancient coastlines will one day reveal communities living through the eruption itself. Perhaps future sediment cores will reconstruct regional climates with far greater precision. Perhaps ancient genomes recovered from tropical environments once considered impossible to preserve will transform understanding of prehistoric population movements. Science advances through such possibilities. Meanwhile, the eruption offers a perspective extending far beyond prehistory. Modern civilization often feels technologically insulated from natural disasters. Satellites monitor weather systems. Global communication networks transmit warnings within seconds. International aid crosses continents by air. Medical knowledge saves lives unimaginable to earlier generations. Yet the Earth beneath modern civilization remains the same restless planet. Volcanoes continue erupting. Earthquakes continue reshaping landscapes. Glaciers continue melting and advancing according to changing climates. Continents continue drifting, the too slowly for human perception. The geological engine responsible for Toba never stopped operating. Its rhythms simply unfold across timescales that rarely intersect with individual lives. This realization encourages humility. Human history frequently emphasizes kings, empires, inventions, and wars. Geological history reminds us that civilizations exist within much larger planetary systems, capable of altering environments with astonishing speed. The greatest forces shaping our past are often those that no society can command. Yet the Toba story carries another message alongside humility. It is also a story of resilience. Whether humanity is reduced dramatically in number, or simply forced to adapt under immense pressure, the outcome remains extraordinary. Small communities survive changing climates, shifting ecosystems, uncertain food supplies, and landscapes transformed by one of Earth's largest known eruptions. They continue raising children, sharing knowledge, refining tools, exploring new territories, and passing accumulated experience from one generation to the next. Their achievements are almost invisible. They build no pyramids. They carve no monuments. They leave no written records. Instead, they preserve something far more enduring. They preserve the future. Every language spoken today, every city ever built, every scientific discovery, every work of art, every civilization that eventually rises across the globe depends upon those forgotten populations continuing to exist through one difficult age after another. Standing beside Lake Toba now, it becomes easier to appreciate how deceptive landscapes can be. Peaceful water conceals unimaginable violence. Fertile soil originates from devastation. Ancient ash becomes the foundation for new forests. A place once associated with destruction ultimately supports thriving ecosystems and human communities. The Earth repeatedly demonstrates that endings and beginnings are often separated only by time. The volcano that may have tested humanity so profoundly no longer threatens the scattered bands of hunter-gatherers who once wandered the late Pleistocene world. Those people are gone. Their names have vanished. Their camps have disappeared beneath soil and vegetation, but their descendants remain. Every person alive carries forward the inheritance of ancestors who endure an unpredictable planet. Whether they survive Toba countless ice age winters, prolonged droughts changing coastlines, or challenges still hidden from the archaeological record, they prove that the defining strength of Homo sapiens is not certainty, nor physical power, nor even intelligence alone. It is the quiet determination to adapt when the world refuses to stay the same. The waters of Lake Toba continue their quiet rhythm long after the echoes of the eruption have faded beyond memory. Wind moves gently across the surface. Rain falls, rivers flow into the great basin, and forests climb the surrounding hills once more. The landscape no longer announces its violent past. Instead, it offers the illusion that it has always been this peaceful, as though the earth has forgotten what happened here. Yet memory does not exist only in stories. It survives in layers of ash buried beneath distant valleys, in microscopic particles resting on the floor of ancient lakes, in fragments of stone shaped by careful hands, and in the shared genetic inheritance carried by every living person. These are quiet memories requiring patience rather than imagination. Piece by piece they remind us that the deepest chapters of human history are often written without words. The people who lived through that distant age could never know the significance of their own survival. They did not see themselves as the ancestors of future civilizations. They simply searched for water, gathered food, protected their children, and adapted to a world that refused to remain predictable. Every successful season allowed another generation to be born. Every lesson learned beside a fire became part of an invisible chain stretching forward across thousands of centuries. The volcano itself became only one moment in that much longer journey. The ash settled. Forests slowly returned. Animals found new paths across changing landscapes. Rivers carved fresh channels through volcanic deposits. What once appeared to be an ending gradually became another beginning, as life reclaimed even the most devastated ground with remarkable patience. Perhaps that is the most enduring lesson hidden within this ancient catastrophe. Earth has always been a changing world. Mountains rise and disappear, coastlines move, climates shift, entire ecosystems transform over spans of time far longer than any individual life. Humanity has never existed apart from those changes. From the very beginning, our ancestors survived not because the world became safer, but because they learned generation after generation to adapt when it did not. Looking across Lake Toba today, it becomes difficult to separate destruction from renewal. The calm water owes its existence to unimaginable violence. The fertile soil surrounding the lake is the weathered remains of volcanic ash. Beauty and catastrophe occupy the same landscape, separated only by time, and perhaps that is the quiet truth preserved beneath the rocks. History is not only the story of civilizations that rose and fell, or of disasters that reshaped continents. It is also the story of ordinary people whose names are forever lost, yet whose perseverance carried humanity through one uncertain age after another. Their footprints have vanished, their voices have fallen silent, but the world they left behind continues to whisper through stone, ash, and water. The volcano changed the earth. Whether it changed human evolution as profoundly as some theories suggest will remain a question that science continues to explore. But one fact is beyond doubt: our species endured. And in that endurance lies one of the oldest and most remarkable stories the planet has ever preserved.